Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the quiet forces that shaped our world in ways we never noticed. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The Earth breathes in ways we cannot see. 4.5 billion years ago, as our planet spins in its early orbit, invisible architects begin their work. The gravitational pull of distant Jupiter, the subtle tug of a young Mars, the steady presence of Venus, all of these worlds reach across the darkness with forces so gentle they barely register as whispers. Yet these whispers carve continents. In laboratories today, scientists measure gravitational resonances that operate on scales almost too small to detect, a millionth of Earth's own gravitational field. The kind of force that might nudge a grain of sand across a table over the course of a human lifetime. But deep time transforms whispers into symphonies. Over millions of years, these microscopic tidal forces massage the bedrock itself, creating stress patterns that influence where fault lines will eventually form, where mountain ranges will rise, where valleys will sink toward the sea. The gravitational field equations that describe these interactions fill pages with mathematical symbols that look more like poetry than physics. Terms for planetary mass: distance cubed, orbital resonance, tidal dissipation. Each symbol represents a force so subtle that early geologists dismissed the possibility entirely. How could Mars, 40 million miles away at its closest approach, possibly influence the solid rock beneath our feet? How could Jupiter, separated from Earth by the vast emptiness of the asteroid belt, leave fingerprints in our mountain ranges? The answer lies in the patient accumulation of almost nothing. Each day, the gravitational pull of Mars on Earth's continental crust amounts to roughly the weight of a single raindrop spread across an entire city. Each rotation of our planet subjects the bedrock to a tidal stress equivalent to someone pressing gently on a granite monument with the tip of their finger. These forces seem laughably insignificant until multiplied by millions of days, billions of rotations, countless orbital cycles stretching across geological ages. Modern precision gravimeters, instruments so sensitive they can detect changes in Earth's gravitational field caused by the movement of groundwater beneath the surface, reveal the ongoing dance between worlds. These devices record minute fluctuations that correspond to the positions of other planets. Tiny gravitational tugs that flex the solid Earth by mere micrometers. The measurements require correction for everything from atmospheric pressure changes to the gravitational pull of distant mountains. Yet the planetary signals persist in the data like a cosmic heartbeat. The mystery lies not in the forces themselves. Physicists can calculate these interactions with remarkable precision, but in their cumulative effects across geological time. Computer models struggle to predict exactly how a billion years of gentle gravitational massage might reshape a continent. The mathematics becomes so complex that even our most powerful supercomputers can only approximate the dance. The differential equations that govern planetary tidal forces contain terms that grow exponentially over time, creating what mathematicians call chaotic behavior. Small changes in initial conditions can lead to vastly different outcomes over geological timescales. Deep beneath the Pacific Ocean, sediment cores reveal layers of microscopic organisms that lived and died during the Cretaceous period, some 100 million years ago. Within these ancient layers, scientists find subtle variations in the types of shells and skeletons preserved. The chemistry of these tiny fossils reflects the temperature and chemistry of ancient seawater, which, in turn, reflects the patterns of ocean circulation that existed when these creatures were alive. And these circulation patterns, researchers now understand, were influenced by the gradual changes in Earth's orbit caused by the gravitational pulls of other worlds. Only took 4 billion years to build the Rockies, the models suggest, with a kind of cosmic patience that makes glaciers seem hurried. Only took a few 100 million rotations around the Sun to nudge the Pacific Plate into its current position. Only took the combined gravitational influence of every planet in the solar system, working together like the world's quietest construction crew, to create the geography that would eventually cradle the first stirrings of life. The Himalaya rise at roughly the same rate that human fingernails grow, driven by tectonic forces that respond, in part, to gravitational resonances established when the solar system was young. In the Canadian Arctic, geologists study rock formations that preserve evidence of ancient mountain-building events. These rocks contain minerals that formed under specific conditions of temperature and pressure, conditions that existed deep within the Earth's crust during periods of intense geological activity. The timing of these mountain-building episodes, scientists now realize, correlates with periods when Earth's orbit brought it into gravitational resonance with Jupiter and Saturn, creating enhanced tidal forces that stressed the planet's crust and triggered episodes of tectonic activity. Modern seismologists occasionally detect these planetary influences in their most sensitive instruments, deep beneath our feet. The solid rock of the continents flexes and flows like thick honey, responding to gravitational pulls from worlds millions of miles away. The effect is so subtle that it requires decades of data collection to even notice the pattern. Seismic stations in Antarctica, isolated from the vibrations of human activity, record the planet's response to gravitational forces with extraordinary precision. The data shows that Earth's crust rises and falls by mere millimeters in response to the changing positions of other planets, a cosmic breathing that continues today as it has for billions of years. The most precise measurements come from laser ranging experiments, where scientists bounce light off reflectors placed on the Moon by Apollo astronauts. By timing the return of these laser pulses with extraordinary accuracy, researchers can track the Moon's position to within centimeters. These measurements reveal not only the Moon's gradual recession from Earth, but also the subtle perturbations in its orbit caused by the gravitational influence of other planets. The data contains signals from Mars, Venus, Jupiter, even distant Saturn, each world leaving its signature in the Moon's motion like notes in a cosmic symphony. Yet there it is, the invisible architecture of planetary forces, still at work, still shaping the world grain by grain. Mars pulls eastward with the patience of stone, its reddish disk crossing the night sky while its gravity reaches across the darkness to touch our continents. Jupiter's gravity reaches inward like a hand placed gently on the shoulder of Earth. Massive and distant and utterly reliable in its influence. Venus adds her own quiet influence to the cosmic collaboration, her orbital dance creating resonances that echo through the inner solar system. Together, they sculpt a world without ever touching it, building continents from pure mathematics and time, writing the history of our planet in the patient language of gravity and stone. The Earth's magnetic field flickers like a candle in the cosmic wind, 4 billion years ago, as molten iron churns within the planet's core. Electromagnetic forces begin to weave patterns that will influence the chemistry of life itself. The magnetic field lines stretch from pole to pole, creating invisible highways through space. But these pathways are not constant. They shift and waver, strengthen and weaken, creating pockets of different electromagnetic influence across the planet's surface. Deep within the Earth's outer core, liquid iron moves in complex convection patterns, driven by heat flowing outward from the solid inner core. This movement of electrically conductive metal generates electric currents, and these currents produce magnetic fields. The process operates like a vast dynamo, converting the planet's rotational energy and internal heat into electromagnetic force. But the dynamo is not perfectly stable. Variations in the core's temperature, changes in the rate of heat flow, fluctuations in the planet's rotation. All of these factors cause the magnetic field to vary in strength and direction over timescales ranging from years to millions of years. Modern paleomagnetic studies reveal the ancient history of these variations. When volcanic rocks solidify, iron-bearing minerals within them align with the Earth's magnetic field, preserving a record of the field's direction and intensity at the moment of cooling. By studying these magnetic fossils in rocks of different ages, scientists have discovered that the Earth's magnetic field has reversed hundreds of times throughout geological history. During these reversals, the field weakens dramatically before reorganizing with opposite polarity. North becomes south. South becomes north. And for brief periods measured in thousands of years, the planet exists with little magnetic protection from cosmic radiation. These magnetic field variations create subtle but important effects on atmospheric chemistry. When the field is strong, it deflects most of the charged particles streaming from the sun, channeling them toward the polar regions where they create the aurora. When the field is weak, more solar particles penetrate deeper into the atmosphere, where they trigger chemical reactions that would not otherwise occur. Nitrogen and oxygen molecules, broken apart by high-energy particles, recombine in different ways, creating trace amounts of nitrous oxides, ozone, and other reactive compounds. The mystery lies in understanding exactly how these electromagnetic variations influence the development of early life. Computer models suggest that periods of weak magnetic field might have increased the production of certain organic compounds in the upper atmosphere. Compounds that could then settle to the surface and contribute to the chemical processes that eventually led to living organisms. Other models propose that magnetic field variations affected the formation of protective ozone layers, creating windows of time when ultraviolet radiation could reach the surface and drive photochemical reactions essential for early biochemistry. In the Pilbara region of Western Australia, geologists study some of the oldest rocks on Earth, formations that preserve evidence of conditions that existed more than 3 billion years ago. These ancient rocks contain layers of iron-rich minerals that formed when dissolved iron in the early oceans was oxidized and precipitated to the sea floor. The patterns within these iron formations suggest that the oxidation process was not uniform across the planet's surface, but occurred in patches and bands that correspond to regions of different magnetic field intensity. Only took a few 100 million years for the magnetic dynamo to stabilize. The paleomagnetic records suggest, with the kind of geological patience that makes continental drift seem rushed, only took countless reversals and fluctuations for the electromagnetic system to find its rhythm, creating the relatively stable magnetic field that protects our atmosphere today. Only took billions of years of magnetic field variations to help create the chemical conditions necessary for life to emerge and flourish. Each electromagnetic shift contributing to the vast experiment in planetary chemistry that continues around us. The Van Allen radiation belts, discovered during the early space age, demonstrate the ongoing importance of Earth's magnetic field in shaping our planet's electromagnetic environment. These belts consist of charged particles trapped by magnetic field lines, creating regions of intense radiation that spacecraft must navigate carefully. The shape and intensity of these belts vary with solar activity and with changes in the magnetic field itself, creating a dynamic system that responds to both internal and external influences. Modern magnetospheric research reveals the complex interactions between Earth's magnetic field and the solar wind, the stream of charged particles flowing outward from the Sun. When solar particles encounter the magnetic field, they are deflected and channeled, creating a bow shock upstream from Earth like the wake of a ship moving through water. But some particles find ways through the magnetic barrier, following field lines toward the poles or squeezing through regions where the field is compressed or distorted. Recent satellite missions have mapped the magnetic field with unprecedented precision, revealing features that were invisible to ground-based instruments. The field is not uniformly strong across the planet's surface, but varies in complex patterns that reflect the dynamic processes occurring deep within the core. Over the South Atlantic Ocean, a region known as the South Atlantic Anomaly shows significantly weaker magnetic field strength, allowing cosmic radiation to penetrate closer to Earth's surface. The aurora themselves provide a visible manifestation of these electromagnetic processes. When charged particles from space follow magnetic field lines toward the poles, they collide with atoms and molecules in the upper atmosphere, causing them to emit light. The colors depend on the type of atoms involved and the altitude at which the collisions occur. Oxygen produces the familiar green and red colors, while nitrogen contributes blue and purple hues. The patterns of auroral displays reflect the structure of the magnetic field lines, creating curtains and arcs of light that reveal the invisible architecture of electromagnetic force. Archaeological studies of ancient pottery and hearthstones show that humans have unknowingly recorded magnetic field variations for thousands of years. When clay is heated to high temperatures, iron minerals within it realign with the magnetic field. By measuring the magnetic orientation preserved in pottery fragments from different time periods, scientists can track how the field has changed during human history. These studies reveal that the field has weakened by about 10% over the past 150 years, possibly indicating that another magnetic reversal may be approaching. Yet the magnetic field continues its ancient work, invisible and essential, shaping the chemistry of our atmosphere with the same electromagnetic forces that have operated for billions of years. The field lines stretch through space like the strings of a vast instrument, vibrating with the solar wind, resonating with cosmic forces, playing the quiet music of electromagnetic interaction that has helped create the conditions for life on our planet. Jupiter wanders through the outer darkness like a shepherd tending invisible flocks. 5 billion years ago, as the solar system settles into its current configuration, the giant planet begins a slow migration that will reshape the orbits of every world in its gravitational domain. This movement is so gradual that if human observers could watch from the beginning of time, Jupiter would appear motionless against the stars for millions of lifetimes. Yet, this apparent stillness conceals one of the most profound influences on Earth's climate and the eventual emergence of life. The migration occurs through gravitational interactions with the disk of gas and dust that surrounded the young Sun. As Jupiter moves through this primordial material, it experiences a subtle drag force, like a ship moving through thick water. This drag causes the planet to spiral slowly inward toward the Sun. But the process is complicated by the presence of Saturn, whose own gravitational influence creates a complex dance of orbital resonances. When the two giant planets reach certain mathematical relationships in their orbital periods, their combined gravitational effects can reverse the direction of migration, sending Jupiter back toward the outer reaches of the solar system. Modern computer simulations of early solar system evolution reveal that Jupiter may have migrated inward to within the current orbit of Mars before reversing course and moving outward again. This inward journey, followed by outward retreat, is known as the Grand Tack model, named for the sailing maneuver where a ship changes direction by moving the bow through the wind. The timing and extent of this migration profoundly influenced the formation and final orbits of the inner planets, including Earth. As Jupiter moves through its ancient migration, it subtly alters Earth's orbital eccentricity through gravitational perturbations that accumulate over millions of years. Earth's orbit is not a perfect circle but an ellipse, and the shape of this ellipse changes cyclically over periods of roughly 100,000 years. These variations, known as Milankovitch cycles, affect how much solar radiation reaches different parts of Earth's surface during different seasons, driving long-term changes in climate patterns. The gravitational influence of Jupiter's migration creates additional complexity within these orbital cycles. When Jupiter was closer to the Sun during its inward migration phase, its gravitational pull enhanced the eccentricity variations in Earth's orbit. When the giant planet moved outward again, it damped these variations, creating periods of more stable orbital geometry. These changes in Earth's orbital behavior influenced seasonal patterns and climate variability over geological timescales, creating windows of stability and instability that may have affected the pace of biological evolution. Deep ocean sediment cores from the Pacific and Atlantic basins preserve chemical evidence of these ancient climate cycles. Within layers of microscopic marine fossils that accumulated on the sea floor over millions of years, scientists find variations in oxygen isotope ratios that reflect changes in ocean temperature and ice volume. These isotopic signatures show cyclical patterns that correspond to Earth's orbital variations, but with subtle irregularities that reflect the complex gravitational influences of the migrating giant planets. The mystery lies in understanding exactly how Jupiter's migration affected the delivery of water and organic compounds to the early Earth. Computer models suggest that the giant planet's changing position influenced the orbits of asteroids and comets in the outer solar system, determining which of these small bodies would eventually collide with Earth. Some models propose that Jupiter's outward migration helped protect the inner solar system from excessive bombardment, while others suggest that specific phases of the migration enhanced the delivery of water-rich comets from the outer regions. Only took a few 100 million years for Jupiter to complete its migration journey. The orbital mechanics calculations suggest, with the kind of celestial patience that makes tectonic drift seem hasty, only took countless gravitational interactions with Saturn and the primordial disk to establish the current architecture of the solar system, creating the orbital relationships that govern planetary motion today. Only took Jupiter's slow dance through space to help create the stable orbital conditions that allowed Earth to develop the long-term climate patterns necessary for life to evolve and diversify. In the asteroid belt between Mars and Jupiter, scientists find evidence of this ancient migration in the current distribution of rocky debris. The belt contains gaps known as Kirkwood gaps, regions where gravitational resonances with Jupiter prevent asteroids from maintaining stable orbits. The pattern of these gaps reflects Jupiter's current position, but computer simulations show that different gap patterns would have existed during the migration phases, creating different populations of asteroids with different probabilities of collision with the inner planets. Modern observations of exoplanetary systems reveal that giant planet migration is common throughout the galaxy. Many stars are orbited by Jupiter-sized worlds that have migrated inward to positions very close to their parent stars, creating a class of planets known as hot Jupiters. These observations suggest that our solar system's architecture, with Jupiter remaining in the outer regions, may be relatively unusual and may have been crucial for creating the conditions that allowed rocky planets like Earth to form and maintain stable orbits. The Juno mission, currently orbiting Jupiter, provides new insights into the giant planet's internal structure and magnetic field. These measurements reveal that Jupiter's core is less dense and more diffuse than previously expected, suggesting that the planet experienced significant changes during its formation and early evolution. The gravitational field measurements from Juno also provide precise data on Jupiter's current mass distribution, which improves calculations of how the planet's migration affected the rest of the solar system. Laser interferometry experiments on Earth can detect the tiny gravitational waves that ripple through space when massive objects accelerate. While these instruments are primarily designed to detect waves from colliding black holes and neutron stars, they are sensitive enough to measure the gravitational effects of Jupiter's motion around the Sun. These measurements provide real-time data on the gravitational forces that continue to shape planetary orbits billions of years after the initial migration ended. The gravitational influence of Jupiter extends far beyond its immediate neighborhood through a phenomenon known as secular resonances. These are slow, long-term changes in orbital elements that occur when planets interact gravitationally over millions of years. Earth's orbit participates in several secular resonance cycles with Jupiter, creating complex patterns of orbital change that affect climate on geological timescales. Some of these resonances may have contributed to major climate transitions in Earth's history, including ice age cycles and periods of rapid warming. Yet Jupiter continues its patient watch from the outer darkness, its massive presence stabilizing the orbits of the inner planets, while its gravitational field shepherds comets and asteroids through their ancient routes. The giant planet's migration journey ended billions of years ago, but its gravitational influence continues to shape Earth's orbital dance, creating the seasonal rhythms and climate cycles that have provided the stable foundation for 4 billion years of biological evolution. Invisible rivers flow through ancient skies, carrying moisture across continents that exist only in the geological memory of stone. 3 billion years ago, as the first stable landmasses rise from primordial seas, atmospheric circulation patterns begin to establish the invisible highways that will determine where water flows, where deserts form, and where the earliest experiments in terrestrial life might find refuge from the harsh chemistry of an alien world. The atmosphere moves in vast cells of circulation driven by the uneven heating of Earth's surface. Warm air rises at the equator, carrying moisture high into the atmosphere before spreading toward the poles and sinking back to the surface in predictable bands. But the pattern is not simple or uniform. The rotation of the planet deflects these air masses through the Coriolis force, creating spiraling currents that curve eastward and westward as they flow between regions of high and low pressure. The positions of continents and oceans further complicate the circulation, creating regional patterns of wind and weather that persist for millions of years. Modern climate models reveal how sensitive these atmospheric rivers are to the arrangement of land and sea. When continents cluster near the equator, they disrupt the normal patterns of tropical circulation, creating intense monsoon systems that can carry moisture thousands of miles inland. When large land masses exist at high latitudes, they create continental climates with extreme seasonal variations, driving atmospheric circulation patterns that extend their influence across entire hemispheres. During Earth's early history, when continental configurations were dramatically different from today, these atmospheric highways followed routes that no longer exist. Paleoclimate studies of ancient sedimentary rocks preserve chemical evidence of these vanished circulation patterns. Layers of sandstone and mudstone that formed in ancient river systems contain isotopic signatures that reflect the source of their water. Some of these signatures indicate that rivers in what is now the Australian outback once carried water that originated as snow falling on mountain ranges that existed near the South Pole. Other isotopic evidence suggests that rainfall in ancient North America was influenced by evaporation from tropical seas that covered much of what is now the Sahara Desert. The mystery lies in understanding how these atmospheric rivers influence the distribution of chemical ingredients essential for early life. Water carries more than just moisture as it moves through the atmosphere. Dissolved in raindrops and snow crystals are trace amounts of minerals, gases, and organic compounds that determine the chemistry of the environments where precipitation falls. Atmospheric circulation patterns act as vast sorting mechanisms, concentrating some chemical species in certain regions while depleting them in others. In the Pilbara Craton of Western Australia, geologists study sedimentary formations that preserve evidence of atmospheric circulation patterns from the Archean eon. These rocks contain layers of chemical precipitates that formed in ancient lakes and shallow seas, preserving records of the trace elements and isotopic compositions of the water that filled these basins. The chemical signatures suggest that this water arrived through atmospheric circulation patterns that carried moisture from volcanic regions thousands of miles away, creating chemical environments that may have been crucial for early biochemical processes. Only took a few 100 million years for stable atmospheric circulation patterns to develop. The climate models suggest, with the kind of meteorological patience that makes seasonal weather seem frantic, only took countless interactions between wind patterns, ocean currents, and continental positions to establish the atmospheric highways that would channel the raw materials of life to the places where chemistry could experiment with the boundary between living and non-living processes. Only took the slow dance of air masses across the face of the planet to create the chemical diversity that early life required to begin its exploration of biological possibility. The Walker Circulation, a massive atmospheric circulation pattern that spans the Pacific Ocean, demonstrates how these ancient atmospheric rivers continue to influence global climate today. This circulation consists of air rising over the warm western Pacific, flowing eastward at high altitude, sinking over the cooler eastern Pacific, and returning westward at low altitude. Variations in this circulation pattern affect weather patterns across the entire Pacific Basin and beyond, influencing rainfall patterns from Australia to South America. Atmospheric scientists use isotopic analysis of water vapor to trace the paths that moisture follows as it moves through modern circulation patterns. By measuring the ratios of heavy and light oxygen isotopes in water samples collected from different locations, researchers can determine where the water originally evaporated and how it traveled through the atmosphere before falling as precipitation. These studies reveal that some rainfall in the Amazon basin originates from evaporation over the Atlantic Ocean thousands of miles away, while other rain comes from moisture recycled through evaporation and transpiration within the rainforest itself. High-altitude jet streams create narrow bands of fast-moving air that can transport moisture and chemical species across entire continents in a matter of days. These rivers of air, flowing at altitudes of 30,000 feet or more, follow paths that are influenced by the positions of mountain ranges, the temperature differences between land and sea, and the seasonal patterns of solar heating. During Earth's early history, when continental positions and atmospheric composition were different, jet stream patterns would have followed different routes, creating different patterns of chemical transport and deposition. Volcanic eruptions provide natural experiments in atmospheric circulation, injecting massive quantities of gases and particles into the atmosphere and allowing scientists to observe how these materials are transported by air currents. The 1815 eruption of Mount Tambora in Indonesia ejected enough material into the stratosphere to affect global climate for several years, creating atmospheric circulation patterns that carried volcanic ash around the world multiple times. Similar eruptions during Earth's early history would have created temporary atmospheric rivers carrying volcanic gases and particles to regions far from their sources. The monsoon systems that bring seasonal rainfall to much of Asia and Africa represent some of the most powerful atmospheric circulation patterns on the planet. These systems reverse direction seasonally, creating alternating periods of wet and dry conditions that affect billions of people today. During Earth's early history, when continental configurations were different, monsoon-like circulation patterns would have existed in different locations, creating seasonal patterns of chemical transport that influenced the environments where early life evolved. Satellite observations of atmospheric water vapor reveal the three-dimensional structure of atmospheric rivers as they flow around the globe. These observations show narrow corridors of enhanced moisture that can extend thousands of miles in length while being only a few hundred miles wide. The moisture within these atmospheric rivers is transported from tropical oceans toward higher latitudes, where it falls as precipitation and influences local climate patterns. Similar atmospheric rivers existed throughout Earth's history. Though their paths and intensities varied with changing continental positions and atmospheric composition, desert dust storms demonstrate how atmospheric circulation can transport solid materials over vast distances. Every year, millions of tons of dust from the Sahara Desert are carried across the Atlantic Ocean by trade winds, providing nutrients to rainforests in South America and influencing ocean chemistry in the tropical Atlantic. During Earth's early history, when different deserts existed in different locations, similar dust transport patterns would have distributed mineral nutrients and possibly organic compounds to regions where early life was experimenting with biochemical innovation. Yet these invisible rivers continue their ancient work, carrying moisture and chemistry through the three-dimensional ocean of air that surrounds our planet. The atmospheric circulation patterns that exist today are different from those that existed billions of years ago, but the fundamental processes remain the same. Air heated by the sun rises and spreads, carrying with it the chemical ingredients that life requires, following the invisible highways of pressure and wind that connect every point on Earth's surface to every other point through the patient circulation of the atmosphere. Deep within the Earth's crust, crystals hum with frequencies too low for human ears to detect. Across billions of years, as minerals form and deform under immense pressures, they generate tiny electrical fields through a process known as the piezoelectric effect. When mechanical stress is applied to certain crystal structures, electric charges separate within the mineral lattice, creating voltage differences that can influence the chemistry of surrounding materials in ways that scientists are only beginning to understand. The piezoelectric effect was first discovered in quartz crystals during the late 19th century, but its presence in crustal rocks extends back to the earliest moments of Earth's geological history. As tectonic forces compress and stretch the planet's crust, vast formations of piezoelectric minerals experience mechanical stress that converts directly into electrical energy. Quartz, the most abundant mineral in continental crust, exhibits strong piezoelectric properties, as do feldspar, tourmaline, and many other common rock-forming minerals. The cumulative electrical output from these natural crystal formations may have created electrical environments that influenced early biochemical processes. Modern geophysical surveys detect these naturally occurring electrical fields in crustal rocks around the world. Magnetotelluric measurements, which probe the electrical conductivity of subsurface materials, reveal complex networks of electrical activity within the solid Earth. Some of this electrical activity results from the movement of ionic solutions through rock pores and fractures, but a significant component appears to originate from piezoelectric effects in stressed minerals. The electrical signatures are strongest in regions of active tectonism, where ongoing deformation continuously generates new piezoelectric charges. Laboratory experiments demonstrate that piezoelectric fields can catalyze certain organic chemical reactions that would not otherwise occur under purely thermal conditions. When amino acids and simple organic compounds are exposed to electrical fields similar to those generated by stressed crystals, they undergo polymerization reactions that create longer molecular chains resembling the building blocks of proteins and nucleic acids. The electrical fields appear to provide the activation energy necessary for these reactions to proceed at temperatures and pressures that would have existed in Earth's early crust. The mystery lies in determining exactly how widespread these piezoelectric effects were during the Archean and Proterozoic eons, when life was first emerging on Earth. Computer models suggest that the higher levels of tectonic activity that characterize the early Earth would have generated more intense and widespread piezoelectric fields than exist today. The increased heat flow from the planet's interior would have driven more vigorous convection in the mantle, creating more frequent and intense episodes of crustal deformation that would have stressed piezoelectric minerals throughout the continental masses. In the Barberton Greenstone Belt of South Africa, geologists study some of the oldest preserved crustal rocks on Earth, formations that date back more than 3 billion years. These rocks show evidence of intense deformation and metamorphism that would have generated significant piezoelectric effects during their formation. Within the same rock formations, researchers find some of the earliest chemical evidence for life on Earth, including carbon isotopic signatures that suggest biological processes were active in these electrically charged environments. Only took a few billion years of tectonic stress to create the complex networks of electrical activity that permeate the continental crust today. The geophysical surveys suggest, with the kind of geological patience that makes lightning seem instantaneous, only took countless episodes of mountain building, fault movement, and crustal deformation to establish the piezoelectric infrastructure that may have provided the electrical environments where chemistry first learned to distinguish between left-handed and right-handed molecules. Only took the patient accumulation of crystal stress to create electrical fields that could nudge organic reactions toward the complex molecular architectures that life requires. The phenomenon of earthquake lights provides dramatic evidence of the electrical activity generated by crustal deformation. Before and during some earthquakes, observers report seeing unusual lights in the sky, ranging from brief flashes to sustained glowing phenomena that can last for several minutes. Scientific investigation of these reports suggests that the lights result from electrical charges generated by piezoelectric effects in quartz-rich rocks as they fracture and deform during seismic activity. The electrical charges can be sufficient to create atmospheric discharges similar to lightning, demonstrating the significant voltages that can be generated by purely geological processes. Hydrothermal systems in volcanic regions create natural laboratories where the interaction between electrical fields and organic chemistry can be observed directly. Hot springs and geysers often contain dissolved minerals and organic compounds that interact with electrical fields generated by stressed volcanic rocks. Some of these hydrothermal environments show enhanced concentrations of complex organic molecules compared to what would be expected from purely thermal chemical processes, suggesting that electrical effects may contribute to organic synthesis in these settings. Laboratory studies of mineral-water interfaces reveal that piezoelectric effects can influence the behavior of organic molecules adsorbed on crystal surfaces. When mechanical stress is applied to piezoelectric minerals in contact with organic solutions, the resulting electrical fields can orient polar molecules in specific ways, potentially promoting particular reaction pathways. This surface chemistry effect could have been important in early Earth environments where organic compounds came into contact with stressed minerals in fracture zones and fault systems. The global electrical circuit of the atmosphere provides a modern analog for understanding how electrical phenomena might have influenced early Earth chemistry. Lightning generates roughly 100 lightning strikes per second worldwide, creating electrical currents that flow through the atmosphere and ground, connecting electrically active regions across the planet. During Earth's early history, when atmospheric composition was different and tectonic activity was more intense, similar electrical circuits would have operated with different intensities and patterns. Modern seismic networks detect ultra-low frequency electromagnetic signals that precede some earthquakes by days or weeks. These signals appear to originate from piezoelectric effects in crustal rocks as they approach failure under tectonic stress. The electromagnetic precursors can be detected by sensitive instruments hundreds of miles from the eventual earthquake epicenter, demonstrating that piezoelectric effects in the crust can generate electromagnetic signals that propagate over continental distances. Biomineralization processes in modern organisms provide insights into how electrical fields might have influenced early biochemistry. Many organisms, from bacteria to vertebrates, precipitate minerals within biological structures through processes that involve electrical control of crystal growth. The organisms use biological electrical fields to control the size, shape, and orientation of mineral crystals, suggesting that similar electrical control mechanisms might have operated during the prebiotic period when mineral surfaces were catalyzing organic reactions. The discovery of natural nuclear reactors in ancient rocks from Gabon, Africa, demonstrates that geological processes can generate electrical phenomena on scales that influence regional chemistry for millions of years. These ancient reactors operated roughly 2 billion years ago when natural uranium concentrations were higher than they are today. The nuclear fission generated intense heat and radiation that created unique mineral assemblages and chemical environments over areas spanning several square kilometers, showing how geological electrical phenomena can create distinctive chemical signatures in the rock record, yet the crystals continue their ancient electrical work, responding to each tectonic stress with the generation of minute electrical fields that influence the chemistry of their immediate surroundings. Deep within mountain ranges that rise at rates measured in millimeters per year, vast formations of quartz and feldspar convert mechanical energy into electrical energy with the same fundamental physics that operate in the electronic devices of human technology, creating electrical environments that may have provided the crucial catalytic conditions for life's first tentative steps toward chemical complexity. Mars breathes its ancient atmosphere into the darkness between worlds, a planetary exhalation that carries the memory of magnetic fields that died billions of years ago. Once, the red planet possessed a global magnetic field similar to Earth's, generated by convection currents in its molten core. But Mars is smaller than Earth, and smaller worlds cool more quickly. As the planet's interior solidified and its magnetic dynamo weakened, the protective electromagnetic barrier that had shielded its atmosphere began to fail, leaving the planet vulnerable to the constant stream of charged particles flowing outward from the Sun. The collapse of Mars's magnetic field occurred gradually over hundreds of millions of years, but the consequences extend far beyond the red planet itself. As the solar wind strips away the Martian atmosphere, it creates a wake of charged particles that flows downstream in the solar system's magnetic environment. Earth, orbiting in the inner solar system, occasionally passes through regions of space that contain these remnants of Mars's lost atmosphere, creating subtle but measurable effects on our own planet's upper atmospheric chemistry. Modern spacecraft missions to Mars have mapped the planet's current magnetic environment in unprecedented detail. The Mars Atmosphere and Volatile Evolution mission, known as MAVEN, measures the ongoing atmospheric loss process, and has discovered that Mars continues to lose hundreds of tons of atmosphere to space every day. This atmospheric material doesn't simply disappear, but becomes part of the complex plasma environment that fills the space between planets, creating what scientists call the interplanetary medium. Spectroscopic analysis of the Martian atmosphere reveals isotopic signatures that tell the story of billions of years of atmospheric evolution. The ratio of heavy to light hydrogen isotopes in Martian water vapor is dramatically different from the same ratio in Earth's oceans, indicating that Mars has lost the majority of its original water inventory to space. The heavier isotopes remain preferentially in the planet's thin atmosphere because they are harder for solar wind particles to strip away, creating a progressive enrichment that serves as a chronometer for atmospheric loss. The mystery lies in understanding exactly how particles from Mars's vanishing atmosphere affect Earth's upper atmospheric chemistry when our planet encounters them in interplanetary space. Computer simulations suggest that these Martian particles can trigger cascade reactions in Earth's ionosphere, the electrically charged layer of atmosphere that extends from about 60 to 600 miles above the planet's surface. The ionosphere is sensitive to even small changes in its particle environment, and the introduction of Martian atmospheric components could influence the production of nitric oxide, ozone, and other trace gases that affect atmospheric chemistry. In Antarctica, scientists study ice cores that preserve records of atmospheric chemistry extending back hundreds of thousands of years. Within these ice layers, researchers find variations in the concentrations of certain trace gases that correlate with known astronomical cycles, including the changing distance between Earth and Mars as the two planets follow their elliptical orbits. Some of these correlations might reflect direct chemical influences from Mars's escaping atmosphere, though the effects are so subtle that they require sophisticated analytical techniques to detect. Only took a few 100 million years for Mars to lose most of its magnetic field protection. The magnetometer data suggest, with the kind of planetary patience that makes geological processes seem rushed, only took a few billion more years for the solar wind to strip away most of the planet's atmosphere, creating the thin, cold environment that exists today. Only took the slow death of one world's magnetic field to create a subtle but ongoing influence on the atmospheric chemistry of its neighboring planet, connecting the fates of two worlds across the emptiness of interplanetary space. The solar wind itself varies in intensity and composition over timescales ranging from minutes to decades. During periods of high solar activity, the increased particle flux accelerates atmospheric loss from Mars and creates more intense populations of charged particles in interplanetary space. These variations in solar wind intensity are recorded in the isotopic compositions of meteorites and in the geological records of both planets, creating a shared history of solar influence that connects the atmospheric evolution of all the inner planets. Numerical models of interplanetary particle transport reveal the complex three-dimensional structure of the charged particle environment between planets. Mars's escaping atmosphere creates spiral streams of particles that follow the magnetic field lines embedded in the solar wind, creating helical structures that can extend millions of miles downstream from the planet. Earth periodically encounters these particle streams as it orbits the Sun, particularly when the orbital geometries align in specific configurations. The Martian meteorites found on Earth provide direct physical samples of the red planet's atmospheric history. These rocks, blasted from Mars by asteroid impacts and delivered to Earth after millions of years of interplanetary travel, contain trapped bubbles of ancient Martian atmosphere. Analysis of these atmospheric samples reveals isotopic compositions that differ from the current Martian atmosphere, documenting the chemical evolution of the planet's air over geological time. Laboratory experiments demonstrate that when charged particles from space interact with Earth's upper atmosphere, they can create chemical species that would not form under normal atmospheric conditions. High-energy particles break apart molecular nitrogen and oxygen, creating reactive fragments that recombine in unusual ways. Some of these reactions produce trace amounts of organic compounds that eventually settle to Earth's surface, potentially contributing to the inventory of organic molecules available for early biochemical processes. The aurora displays that occur in Earth's polar regions provide visible evidence of ongoing interactions between our planet and the charged particle environment of interplanetary space. When particles from the solar wind, including components that may have originated from Mars's escaping atmosphere, follow Earth's magnetic field lines toward the polar regions, they collide with atmospheric gases and cause them to emit light. The colors and patterns of auroral displays reflect the energy and composition of the incoming particles, creating a natural display that connects Earth's atmosphere to the broader particle environment of the solar system. Satellite measurements of Earth's magnetosphere reveal periodic variations that correlate with the changing positions of Mars and other planets in their orbits around the Sun. These variations suggest that the gravitational influence of other planets affects the shape and dynamics of Earth's magnetic field, which in turn affects how charged particles from interplanetary space interact with our planet's atmosphere. The effect is subtle but measurable, demonstrating that planetary magnetic fields are connected through the complex electromagnetic environment of the solar system. Radio observations from ground-based telescopes detect electromagnetic emissions from the interaction between Mars and the solar wind. These radio signals, generated when charged particles are accelerated by magnetic fields in the Martian plasma environment, can be received on Earth and analyzed to understand the ongoing atmospheric loss process. The radio emissions vary with solar activity and with the seasonal cycles on Mars, creating a kind of planetary radio broadcast that tells the story of atmospheric escape in real time. Deep space missions have revealed that atmospheric loss is a common process throughout the solar system. Venus, despite its thick atmosphere, loses material to space through different mechanisms than Mars, while the gas giant planets lose atmospheric components through entirely different processes. These observations suggest that atmospheric exchange between planets through interplanetary space may be a fundamental aspect of planetary evolution, connecting the chemical histories of all the worlds in the solar system. Yet Mars continues its patient atmospheric donation to the interplanetary environment, each day losing more of its ancient air to the solar wind, while Earth orbits through the subtle wake of this planetary exhalation. The magnetic field that once protected the red planet is gone, but its influence persists in the charged particle streams that carry Martian atmospheric components through the space between worlds, creating chemical connections that link the evolutionary histories of neighboring planets across the vast scales of astronomical time. The Moon pulls away from Earth with the steadiness of falling sand, each year retreating by the width of a human fingernail. This recession leaves behind a record written in stone, preserved in the rhythmic layers of ancient sedimentary rocks that accumulated in tidal environments billions of years ago. As the Moon slowly spirals outward, the length of Earth's day gradually increases, and the strength of tidal forces weakens, creating subtle changes in the patterns of sediment deposition that geologists can read like the pages of a cosmic calendar. Tidal rhythmites, sedimentary rocks that preserve the daily and monthly cycles of ancient tides, contain some of the most precise records of Earth-Moon dynamics available in the geological record. These rocks formed in shallow marine environments where tidal currents alternately deposited fine and coarse sediments, creating layered sequences that reflect the complex periodicities of tidal cycles. By counting the layers and measuring their thicknesses, scientists can determine how many hours constituted a day and how many days made up a month at various times in Earth's history. The most detailed tidal records come from rock formations that are roughly 620 million years old, deposited during the late Proterozoic era when complex multicellular life was just beginning to diversify. These ancient tidal sequences indicate that at that time, Earth's day was only about 22 hours long, and the lunar month contained approximately 13.5 of these shorter days. The moon was significantly closer to Earth than it is today, creating tides that were dramatically stronger and more frequent than anything experienced in the modern ocean. Modern laser ranging experiments provide precise measurements of the moon's current rate of recession. By bouncing laser pulses off retroreflectors placed on the lunar surface by Apollo astronauts and robotic missions, scientists can track the moon's position to within millimeters. These measurements reveal that the moon is currently receding at a rate of 3.8 centimeters per year, a rate that varies slightly due to changes in Earth's rotation and the configuration of ocean basins that affect tidal energy dissipation. The mystery lies in understanding exactly how the changing tidal environment influenced the evolution of early life. Tidal zones create unique ecological conditions where organisms must cope with regular exposure to both marine and terrestrial environments. The stronger tides of the ancient Earth would have created more extensive intertidal zones and more extreme conditions for any life forms attempting to colonize the boundary between land and sea. Some researchers propose that the intense tidal mixing of the early Earth helped distribute nutrients and organic compounds in ways that promoted biological innovation. In the Bay of Fundy, which experiences some of the strongest tides on the modern Earth, geologists study how tidal energy affects sediment transport and deposition. The bay's funnel shape amplifies tidal forces, creating tide ranges that can exceed 15 meters during spring tides. The sedimentary patterns preserved in the bay's mudflats provide modern analogues for understanding how much stronger ancient tides might have affected coastal environments when the moon was closer and tidal forces were more intense. Only took 4 billion years for the moon to migrate from its initial position to its current distance. The tidal models calculate, with the kind of celestial patience that makes continental drift seem sudden, only took countless tidal cycles, each one slightly weaker than the last, to gradually slow Earth's rotation and lengthen the day from its original duration of perhaps 6 hours to the current 24-hour cycle. Only took the patient gravitational dance between Earth and Moon to create the tidal environments where life first experimented with the challenges of surviving in zones of constant environmental change. The mathematical relationship between tidal force and distance follows an inverse cube law, meaning that small changes in the moon's distance create large changes in tidal strength. When the moon was half its current distance from Earth, tidal forces were 8 times stronger. These ancient supertides would have reached far inland, creating vast tidal flats and lagoons that covered areas that are now dry land. The fossil record from these periods shows evidence of extensive marine environments in locations that are now hundreds of miles from the nearest ocean. Paleomagnetic studies of tidal rhythmites provide additional evidence for changing Earth-Moon dynamics. As sediments accumulate in tidal environments, iron-bearing minerals within them align with Earth's magnetic field. Preserving a record of magnetic field direction at the time of deposition, changes in the rate of sediment accumulation, which correlate with tidal strength, can be detected in the magnetic record and used to reconstruct ancient tidal patterns even when the sedimentary layers themselves have been altered by subsequent geological processes. The discovery of similar tidal rhythmites on other planets would provide crucial evidence for understanding how common Earth-like tidal environments might be throughout the universe. Mars shows evidence of ancient ocean shorelines, and if tidal sediments could be identified in these formations, they would provide information about the presence and orbital characteristics of any ancient Martian moons. The absence of strong tidal indicators in Martian sedimentary rocks might help explain why life, if it ever existed on Mars, did not develop the same level of complexity as terrestrial life. Computer simulations of Earth's early tidal evolution must account for the changing configuration of ocean basins over geological time. Continental drift has dramatically altered the size, depth, and connectivity of ocean basins, which affects how tidal energy is dissipated and therefore influences the rate of lunar recession. During periods when the continents were configured differently, tidal energy dissipation would have been more or less efficient, leading to variations in the Moon's recession rate that are preserved in the geological record. The phenomenon of tidal heating demonstrates how gravitational interactions can generate significant amounts of energy within planetary systems. Jupiter's moons Io, Europa, and Ganymede experience strong tidal forces that heat their interiors and drive geological activity. During Earth's early history, when the Moon was much closer, tidal heating of Earth's interior may have contributed to the planet's thermal budget, affecting the rate of mantle convection and the intensity of volcanic activity. Biological studies of modern tidal zone organisms reveal sophisticated adaptations to the rhythmic environmental changes created by tidal cycles. Many marine organisms have internal biological clocks that are synchronized to tidal periodicities, allowing them to anticipate and prepare for changing conditions. These biological rhythms are so deeply embedded in marine ecosystems that some organisms maintain tidal behavioral patterns even when moved to laboratory conditions where no tidal forces exist. The gravitational interaction between Earth and Moon also affects the planet's axial stability. Computer models show that without the Moon's gravitational influence, Earth's rotation axis would undergo chaotic variations that would create extreme climate changes over geological timescales. The Moon's presence helps stabilize Earth's obliquity, maintaining relatively stable seasonal patterns that may have been crucial for the long-term evolution of complex life. Ancient coral reefs provide another source of information about changing day length and tidal patterns. Fossil corals show growth bands that reflect daily and annual growth cycles. And by counting these bands, paleontologists can determine how many days occurred in a year at different times in the past. Devonian corals, roughly 400 million years old, show approximately 400 daily growth bands per year, confirming that days were shorter when these organisms were alive. Yet the Moon continues its ancient recession, pulling away from Earth with the same gravitational forces that have operated for billions of years. Each night, as moonlight illuminates the landscape with light that has traveled a slightly greater distance than it did the night before, the tidal bulges in Earth's oceans lag slightly behind the Moon's position, creating a torque that gradually transfers angular momentum from Earth's rotation to the Moon's orbital motion, driving the slow separation that has been stretching the gravitational bonds between the two worlds since the beginning of their shared history. Earth orbits the Sun through a field of debris that tells the story of planetary loneliness. For billions of years, meteorites and comets have fallen from space, carrying with them the chemical fingerprints of distant regions of the solar system. Within these cosmic messengers, isotope ratios reveal which volatile compounds, water, carbon dioxide, nitrogen, and organic molecules were available for delivery to the early Earth. The pattern of isotopic signatures suggests that Earth's unique orbital position created a selective filter, determining which types of cosmic debris would contribute to the planet's inventory of life-essential materials. The isotopic composition of noble gases in Earth's atmosphere provides some of the clearest evidence for this selective delivery process. Neon, argon, krypton, and xenon exist as chemically inert gases that do not react with other elements, making them ideal traces for understanding the sources of Earth's atmospheric components. The ratios of different isotopes of these gases in Earth's atmosphere differ significantly from the ratios found in the solar wind or in most meteorite types, indicating that Earth's atmosphere was not simply inherited from the solar nebula, but was assembled through the selective accumulation of materials from specific cosmic sources. Meteorites that fall to Earth today carry isotopic signatures that reflect the regions of the solar system where they originated. Carbonaceous chondrites, which come from the outer asteroid belt, contain high concentrations of water and organic compounds with isotopic compositions that closely match those found in Earth's oceans and biosphere. Iron meteorites, which originate from the cores of differentiated asteroids, contain virtually no volatile compounds but preserve isotopic signatures of the metal-rich planetesimals that contributed to Earth's core formation. The Late Heavy Bombardment, a period of intense meteorite impacts that occurred roughly 3.9 billion years ago, may have been crucial for delivering the final inventory of volatile compounds that made complex chemistry possible on Earth's surface. Computer simulations of solar system dynamics suggest that this bombardment was triggered by orbital changes among the giant planets that destabilize populations of asteroids and comets, sending them on collision courses with the inner planets. The timing of this cosmic delivery coincides with the earliest evidence for life on Earth, suggesting a possible causal relationship between cosmic chemistry and biological innovation. The mystery lies in understanding why Earth received a more favorable mixture of volatile compounds than its planetary neighbors. Mars and Venus presumably experienced similar bombardment histories, but their current inventories of water and atmospheric gases differ dramatically from Earth's. Venus has lost most of its water to space through photodissociation and hydrogen escape, while Mars has lost most of its atmosphere to solar wind stripping. Earth's intermediate position, neither too close to the Sun nor too far away, may have provided the optimal conditions for retaining the volatile compounds delivered by cosmic impacts. In the Sudbury Basin of Ontario, geologists study one of the best-preserved large impact structures on Earth, formed roughly 85 billion years ago when a massive asteroid or comet struck the planet. The impact structure contains unusual rock formations that preserve evidence of the extreme conditions created during the collision. Chemical analysis of these impact rocks reveals that the impacting body was rich in water and organic compounds, demonstrating that even relatively late in Earth's history, cosmic impacts continue to deliver biologically relevant materials to the planet's surface. Only took a few 100 million years of cosmic bombardment to deliver the volatile inventory that would support 4 billion years of biological evolution, the isotopic evidence suggests, with the kind of astronomical patience that makes geological processes seem hurried. Only took countless impacts from asteroids and comets with precisely the right chemical compositions to create the atmospheric and oceanic reservoirs that distinguish Earth from its planetary siblings. Only took Earth's fortunate orbital position to intercept cosmic debris with the isotopic signatures that would prove compatible with the chemistry of life. The delivery mechanism for organic compounds appears to have been particularly important during Earth's early history. Comets and carbonaceous asteroids contain complex organic molecules, including amino acids, nucleotide bases, and other compounds that serve as building blocks for biological macromolecules. When these cosmic objects impact a planet's surface, the organic compounds they contain can survive the impact process if the collision occurs at relatively low velocities, or if the impacting body is large enough that its interior remains relatively cool during the impact. Laboratory experiments demonstrate that organic compounds can survive simulated asteroid impacts under certain conditions. When samples of carbonaceous meteorite material are subjected to shock pressures and temperatures similar to those experienced during impact, Many organic compounds remain intact, though they may undergo chemical modifications that make them more reactive and potentially more useful for prebiotic chemistry. The impact process itself may serve as a kind of cosmic chemistry laboratory, converting simple organic compounds into more complex molecular structures. The isotopic composition of water in Earth's oceans provides crucial evidence for understanding the cosmic sources of Earth's volatile inventory. The ratio of deuterium to hydrogen in seawater is significantly different from the same ratio in the solar nebula, indicating that Earth's water was not inherited directly from the original solar system materials. Instead, the isotopic signature points to sources in the outer solar system, possibly comets or asteroids that formed beyond the orbit of Jupiter and were later scattered inward by gravitational perturbations. Recent analysis of samples returned from asteroid Ryugu by the Japanese Hayabusa 2 mission reveals organic compounds and water with isotopic compositions that closely match those found on Earth. These results provide direct evidence that asteroids from the outer solar system could have delivered both water and organic compounds to the early Earth. The organic compounds found in the Ryugu samples include amino acids and other biomolecules in forms that would have been available for chemical evolution on the early Earth. The chemical composition of Earth's core provides additional evidence for the selective nature of planetary accretion. The core contains significant amounts of sulfur, nickel, and other elements that are depleted in the most common types of meteorites that fall to Earth today. This suggests that the materials that contributed to Earth's core formation had different chemical compositions than the materials that contributed to the planet's later accretion history, reflecting changes in the types of cosmic debris available for planetary construction over time. Atmospheric escape processes demonstrate why Earth's orbital position was crucial for retaining the volatile compounds delivered by cosmic impacts. Planets closer to the Sun experience higher temperatures and more intense solar radiation, which can drive atmospheric escape through thermal processes and photochemical dissociation. Planets farther from the Sun may retain their atmospheres more effectively, but they receive less solar energy to drive the chemical processes necessary for life. Earth's position provides an optimal balance between volatile retention and energy availability. The discovery of organic compounds in meteorites that fall to Earth today shows that the cosmic delivery of biological building blocks continues in the present. The Murchison meteorite, which fell in Australia in 1969, contains more than 70 different amino acids, including many that are not used by terrestrial life. The molecular diversity found in this single meteorite demonstrates the vast chemical laboratory that exists in space and continues to seed planetary surfaces with organic compounds that could serve as raw materials for life. Studies of the lunar surface provide insights into the bombardment history that affected the entire inner solar system. The Moon's surface preserves a record of impact cratering that extends back to the earliest phases of solar system history, providing a timeline for understanding when different types of cosmic debris were most abundant. The chemical composition of lunar impact glasses, formed when meteorites melted lunar surface rocks, preserves isotopic signatures of the impacting bodies and helps reconstruct the sources and timing of volatile delivery to the Earth-Moon system. Yet, Earth continues to move through its unique orbital position, intercepting cosmic debris that carries the isotopic signatures of distant regions of the solar system. Each year, thousands of tons of cosmic material fall to Earth as meteorites and cosmic dust, continuing the process of chemical delivery that has operated for billions of years. The planet's gravitational field and orbital characteristics still act as selective filters, determining which types of cosmic chemistry will contribute to the ongoing evolution of Earth's surface environment and biosphere. Deep beneath the continents, the Earth's core generates vibrations so profound They circle the globe multiple times before dissipating into silence. These seismic whispers, with frequencies lower than the deepest notes of human perception, travel through thousands of miles of solid rock at speeds that make sound through air seem motionless. As they propagate through the planet's interior, these low-frequency waves create standing wave patterns that persist for hours or days, establishing resonant modes that influence geological processes over timescales spanning millions of years. The source of these deep vibrations lies in the convective motions of liquid iron within Earth's outer core. As hot metal rises and cool metal sinks in vast circulation cells, the movement creates pressure waves that propagate through the surrounding solid mantle. The process operates like an enormous musical instrument, with the entire planet serving as a resonating chamber. The fundamental frequency of Earth's deepest oscillations corresponds to vibrations with periods of roughly 20 minutes, meaning that each complete cycle of planetary ringing takes longer than many human activities. Modern seismological networks detect these ultra-low frequency oscillations using broadband seismometers deployed in quiet locations around the world. The Global Seismographic Network maintains stations in remote locations from Antarctica to the Sahara Desert, places where human activity creates minimal interference with the delicate measurements required to detect planetary vibrations. These instruments reveal that Earth is never completely silent, but maintains a continuous background hum of seismic energy that reflects the ongoing thermal and chemical processes operating within the planet's deep interior. Computational studies of seismic wave propagation reveal how these deep vibrations interact with the complex three-dimensional structure of Earth's interior. As seismic waves travel through regions of different temperature, composition, and physical state, they are refracted, reflected, and scattered in ways that create interference patterns. Over geological time, these interference effects can concentrate seismic energy in specific regions, creating zones of enhanced mechanical stress that influence where mineral deposits form and how crustal structures develop. The mystery lies in understanding exactly how these standing wave patterns affect the formation and distribution of economically important mineral deposits. Some of the world's largest ore deposits occur in locations that correspond to nodes of seismic standing wave patterns, regions where constructive interference focuses mechanical energy from deep Earth oscillations. The correlation suggests that seismic focusing may create conditions of enhanced fluid flow and chemical reaction that promote the concentration of metals and other valuable minerals over geological timescales. In the Witwatersrand Basin of South Africa, geologists study gold deposits that formed more than 2 billion years ago in sedimentary rocks that show evidence of periodic hydrothermal alteration. The gold occurs in thin layers that extend for hundreds of miles, suggesting that the mineralizing process is operated over vast areas simultaneously. Recent analysis of the structural geology in the region reveals orientations and spacings that correspond to wavelengths of deep seismic oscillations, supporting the hypothesis that planetary vibrations influence the formation of these ancient treasure deposits. Only took a few billion years of planetary resonance to establish the standing wave patterns that continue to influence geological processes today. The seismic models suggest, with the kind of vibrational patience that makes earthquakes seem like brief interruptions in a vast musical performance, only took countless cycles of core convection and mantle oscillation to create the interference patterns that focus mechanical energy in specific crustal locations where mineral-forming processes can operate with enhanced efficiency. Only took the deep musical architecture of planetary vibration to help concentrate the rare elements that human civilization would eventually discover and depend upon for technological development. The Earth's free oscillations, excited by large earthquakes, provide natural experiments in planetary seismology. When a major earthquake occurs, it sets the entire planet ringing like a struck bell, exciting oscillation modes that can be detected by sensitive instruments for days or weeks after the initial event. Different oscillation modes sample different parts of the planet's interior, providing information about the distribution of density, elasticity, and other physical properties throughout the deep Earth. The study of free oscillations has revealed the existence of seismic anisotropy in the inner core and has provided evidence for chemical layering in the lower mantle. Laboratory experiments on rock samples subjected to cyclic stress demonstrate how low-frequency mechanical oscillations can influence mineral formation and fluid flow processes. When rock samples are exposed to oscillatory stress at frequencies similar to those of Earth's deep vibrations, they show enhanced rates of mineral precipitation and dissolution compared to samples subjected to constant stress conditions. The oscillatory stress appears to promote the formation of fracture networks that facilitate fluid flow, creating pathways for mineralizing solutions to move through otherwise impermeable rocks. The phenomenon of seismic attenuation reveals how mechanical energy is absorbed and dissipated as seismic waves travel through Earth's interior. Different materials absorb seismic energy at different rates, and the pattern of attenuation provides information about the physical state and composition of deep Earth materials. Regions of high attenuation often correspond to areas of elevated temperature or partial melting, while regions of low attenuation typically indicate cold, solid materials. These variations in seismic properties create complex patterns of energy focusing and defocusing that influence where mechanical stress accumulates over geological time. Ancient impact structures provide insights into how large-scale mechanical disturbances can create long-lasting effects on regional geology. The Vredefort impact structure in South Africa, formed by a massive asteroid impact roughly 2 billion years ago, shows evidence of shockwave effects that extend hundreds of miles from the impact site. The distribution of shock metamorphic effects follows patterns that suggest the impact. Generated seismic waves created standing wave patterns that focused mechanical energy in specific locations, influencing subsequent geological processes for millions of years after the impact event. The discovery of seismic anisotropy in Earth's inner core suggests that the solid iron at the planet's center has a preferred crystallographic orientation that affects seismic wave propagation. This anisotropy appears to result from the alignment of iron crystals under the extreme pressure and temperature conditions that exist at the Earth's center. The alignment may be influenced by the convective motions in the outer core and by the magnetic field generated by core dynamics, creating a complex coupling between thermal, mechanical, and electromagnetic processes in the deep Earth. Mineral physics experiments conducted at extreme pressures and temperatures reveal how the properties of Earth materials change under the conditions that exist in the deep interior. These experiments show that many common minerals undergo phase transitions at the pressures and temperatures found in the lower mantle and core, creating discontinuities in seismic wave velocities that affect how mechanical energy propagates through the planet. The locations and properties of these phase transitions influence the focusing and defocusing of seismic energy, contributing to the complex patterns of deep Earth vibration. The study of seismic tomography, which uses earthquake waves to create three-dimensional images of Earth's interior, reveals large-scale structures that affect the propagation of deep oscillations. Subducted oceanic plates, mantle plumes, and other thermal and chemical anomalies create variations in seismic wave velocities that influence how planetary vibrations travel through the interior. These structures act as seismic lenses that can focus or defocus mechanical energy, creating patterns of stress concentration that persist for millions of years. Ocean bottom seismometers deployed on the deep sea floor detect seismic signals that are filtered by their passage through oceanic crust and sediments. These instruments reveal how the mechanical properties of seafloor materials affect the transmission of planetary vibrations from the solid Earth into the overlying water column. The coupling between solid Earth oscillations and ocean acoustic modes creates complex patterns of energy transfer that may influence oceanic circulation and biological processes in ways that are not yet fully understood. Yet the planet continues its deep musical performance, with vibrations generated in the molten iron core traveling through thousands of miles of solid rock to create standing wave patterns that focus mechanical energy in locations where geological processes can concentrate the chemical elements essential for technological civilization. The Earth rings with frequencies too low for human perception, maintaining a constant seismic symphony that has operated for billions of years, shaping the distribution of mineral wealth with the patient mathematics of wave interference and resonance. The continents drift across the planet's surface with the patience of growing mountains, moving at rates that make the erosion of coastlines seem violent and sudden. Driven by convection currents in the molten mantle beneath, vast plates of solid rock slide past, collide with, and separate from each other in a choreographed dance that has been reshaping the geography of Earth for billions of years. This continental ballet operates on timescales so extended that entire mountain ranges rise and fall like slow breathing, each geological inhale and exhale spanning hundreds of millions of years. The mechanism of plate tectonics depends on the unique thermal properties of Earth's interior. Heat generated by radioactive decay of uranium, thorium, and potassium in the mantle creates convection cells that rise toward the surface at mid-ocean ridges and sink back into the depths at subduction zones. The rigid lithospheric plates that carry the continents are passengers on this conveyor belt of solid rock, moving at speeds measured in centimeters per year. The Atlantic Ocean grows wider by roughly the length of a human fingernail each year, while the Pacific Ocean shrinks by a similar amount as oceanic plates are consumed in the deep trenches that ring the Pacific Basin. Modern satellite measurements using global positioning system technology can detect continental motion in real time, revealing that the process continues today with mathematical precision. The measurements show that North America and Europe are separating at a rate of about 2.5 centimeters per year, while Australia moves northward at roughly 7 centimeters per year toward its eventual collision with Asia. These measurements represent the continuation of a process that has been operating for at least 3 billion years, possibly longer, making plate tectonics one of the most persistent geological processes on the planet. Paleomagnetic studies of ancient rocks preserve records of continental positions extending back hundreds of millions of years. As volcanic rocks cool and solidify, iron-bearing minerals within them align with Earth's magnetic field, creating a fossil compass that points toward the magnetic pole that existed at the time of rock formation. By measuring these magnetic orientations in rocks of different ages from the same continent, geologists can track how that continent has moved and rotated over time, revealing paths of continental drift that span entire geological eras. The mystery lies in understanding how the slow dance of continents influences global climate patterns and the evolution of life over geological time. When continents cluster near the equator, they disrupt oceanic circulation and create intense greenhouse conditions. When large land masses migrate to polar regions, they can trigger ice ages that affect global climate for millions of years. The breakup and assembly of supercontinents operates on cycles of roughly 500 million years, creating rhythms of climate change that provide the environmental variability necessary for biological innovation and diversification. In the Himalayas, the ongoing collision between the Indian subcontinent and the Asian mainland demonstrates how continental drift creates the world's most spectacular mountain ranges, India began its northward journey roughly 100 million years ago when it separated from Antarctica and raced across the Indian Ocean at speeds of up to 15 centimeters per year. The collision, which began roughly 50 million years ago, continues today, pushing the Himalayan range higher at rates that slightly exceed the erosional forces trying to wear the mountains down. Only took a few billion years of continental drift to create the current global geography. The paleogeographic reconstructions suggest, with the kind of tectonic patience that makes volcanic eruptions seem like brief moments of geological excitement, only took countless cycles of supercontinent assembly and breakup to establish the distribution of continents and ocean basins that control modern climate patterns and oceanic circulation. Only took the slow collision and separation of crustal plates to create the diverse array of geological environments where life could experiment with different evolutionary strategies over hundreds of millions of years. The Wilson cycle describes the complete life cycle of ocean basins, from initial rifting through mature spreading to eventual closure and continental collision. This cycle operates over timescales of 200 to 500 million years, creating a rhythm of geological change that affects global climate, sea level, and biological evolution. The Atlantic Ocean is currently in the spreading phase of a Wilson cycle, growing wider as new oceanic crust is created at the mid-Atlantic ridge. The Pacific Ocean, by contrast, is in the closing phase, shrinking as oceanic crust is consumed at subduction zones around the Pacific Ring of Fire. Computer simulations of mantle convection reveal the complex three-dimensional structure of the thermal currents that drive plate tectonics. The simulations show that mantle flow is not uniform, but consists of rising and sinking columns of hot and cold rock that create complex patterns of surface motion. Some of these convection cells persist for hundreds of millions of years, creating long-lived patterns of continental drift, while others are more transient, causing periodic changes in the direction and rate of plate motion. The supercontinent cycle represents one of the most important rhythms in Earth's geological history. Roughly every 500 million years, the continents assemble into a single large landmass, then break apart and disperse before eventually reassembling in a different configuration. The most recent supercontinent, Pangaea, began breaking apart roughly 200 million years ago, creating the current distribution of continents. Before Pangaea, earlier supercontinents including Rodinia and Columbia formed and dispersed, each cycle creating different patterns of global geography and climate. Evidence for ancient continental positions comes from matching geological features across modern ocean basins. Mountain belts that formed during ancient continent-continent collisions can be traced across the Atlantic Ocean, connecting the Appalachian Mountains of North America with the Caledonian Mountains of Scotland and Scandinavia. These geological connections provide direct evidence that the Atlantic Ocean is a relatively recent feature in Earth's history, formed by the breakup of Pangaea over the past 200 million years. The process of subduction, where oceanic plates sink back into the mantle, creates some of the most geologically active regions on the planet. As cold oceanic lithosphere descends into the hot mantle, it undergoes metamorphic reactions that release water and other volatile compounds. These fluids rise into the overlying mantle wedge, lowering its melting temperature and creating the magmas that feed volcanic arcs. The subduction process also generates deep earthquakes as the descending plate fractures under the increasing pressure and temperature of the deep earth. Hotspots represent a different type of tectonic process, where stationary plumes of hot mantle material rise toward the surface, creating volcanic activity that is independent of plate boundaries. The Hawaiian island chain provides a classic example of hotspot volcanism, where the Pacific plate has moved over a stationary mantle plume for millions of years, creating a linear chain of volcanic islands that records the plate's motion over the hotspot. Similar hotspot tracks exist throughout the world's oceans, providing additional evidence for the reality and persistence of continental drift. The formation of new oceanic crust at mid-ocean ridges creates a continuous record of Earth's magnetic field history. As molten basalt erupts along the ridge axis and cools, iron-bearing minerals within the rock align with the magnetic field and preserve its direction and intensity. Magnetic surveys of the seafloor reveal symmetrical patterns of magnetic stripes on either side of mid-ocean ridges, recording the history of magnetic field reversals as new oceanic crust was created and moved away from the spreading center. Continental rifting represents the initial stage of continental breakup, where tensional forces begin to tear apart continental lithosphere. The East African Rift System provides a modern example of this process, where the African continent is slowly being split apart by rising mantle plumes. Over millions of years, continued rifting will eventually create a new ocean basin, similar to how the Red Sea formed as Arabia separated from Africa roughly 30 million years ago. Transform faults accommodate lateral motion between tectonic plates, creating linear zones of intense earthquake activity. The San Andreas Fault System in California represents the most famous example, where the Pacific Plate slides past the North American Plate at rates of several centimeters per year. The accumulated motion along transform faults over millions of years can displace geological features by hundreds of miles, demonstrating the enormous cumulative effects of slow but persistent tectonic motion. Yet, the continents continue their ancient migration across the planet's surface, carried by convection currents that operate with the steady persistence of planetary scale circulation. Each year, the dance of plate tectonics moves continents by distances measured in fingernail widths. But the cumulative effect over geological time creates and destroys ocean basins, builds and erodes mountain ranges, and continuously reshapes the global geography that determines where life can flourish and how climate systems operate across the turning Earth. Electric currents flow through the ancient Earth like rivers of invisible lightning, generated by the rotation of iron-rich cores within planetary bodies scattered across the early solar system. 4 billion years ago, as Earth's molten interior churns with convective motion, vast electromagnetic fields emerge from the depths, creating patterns of electrical activity that extend far beyond the planet's surface into the surrounding space. These primordial electrical environments may have provided the organizing forces necessary for the first organic molecules to arrange themselves into the complex architectures that would eventually become the foundation for life. The dynamo process that creates planetary magnetic fields operates through the movement of electrically conductive fluids within rotating planetary cores. As liquid iron moves through existing magnetic fields, it generates electric currents, and these currents in turn create new magnetic fields in a self-sustaining feedback loop. The Earth's magnetic field, generated by this dynamo process, extends tens of thousands of miles into space, creating a magnetosphere that channels charged particles from the solar wind and establishes complex patterns of electromagnetic activity throughout the near-Earth environment. Modern laboratory experiments demonstrate that organic molecules can be influenced by electromagnetic fields in ways that promote the formation of ordered structures. When solutions containing amino acids, nucleotides, and other biological building blocks are exposed to oscillating magnetic fields similar to those that would have existed in the early Earth's electromagnetic environment. The molecules show enhanced rates of polymerization and a tendency to form longer, more complex chains. The electromagnetic fields appear to provide a kind of organizing template that guides molecular assembly processes. Paleomagnetic studies reveal that Earth's magnetic field has varied dramatically in strength and configuration throughout geological history. During some periods, the field was much stronger than today, while during others it was significantly weaker or even absent during magnetic field reversals. These variations in electromagnetic environment would have created different conditions for organic chemistry at different times in Earth's history, possibly influencing the pace and direction of chemical evolution toward increasingly complex molecular systems. The mystery lies in understanding exactly how electromagnetic fields might have influenced the chirality of organic molecules, the property that determines whether biological molecules are left-handed or right-handed in their spatial arrangement. All amino acids used by terrestrial life are left-handed, while all sugars are right-handed, a uniformity that is essential for biological function but difficult to explain through purely chemical processes. Some researchers propose that the electromagnetic environments created by planetary magnetic fields could have provided the asymmetric forces necessary to establish this molecular handedness. In the Izua supracrustal belt of Greenland, geologists study some of the oldest rocks on Earth, formations that preserve chemical evidence of conditions that existed more than 3.7 billion years ago. These ancient rocks contain carbon isotopic signatures that suggest biological processes were active during their formation, but they also contain unusual concentrations of magnetite and other magnetic minerals that indicate intense electromagnetic activity was occurring simultaneously with early biological processes. Only took a few 100 million years for the Earth's magnetic dynamo to establish stable patterns of electromagnetic activity. The paleomagnetic records suggest, with the kind of electrical patience that makes lightning seem momentary, only took countless interactions between magnetic fields and organic molecules to create the conditions where chemistry could begin to distinguish between left-handed and right-handed molecular forms. Only took the patient operation of planetary electrical systems to provide the organizing forces that helped guide the assembly of the first self-replicating molecular systems. The Van Allen radiation belts demonstrate how planetary magnetic fields can trap and concentrate charged particles, creating regions of intense electromagnetic activity that persist for long periods. These belts consist of high-energy protons and electrons that spiral along magnetic field lines, creating standing patterns of electromagnetic energy that remain stable for years or decades. During Earth's early history, when the magnetic field configuration was different, similar radiation belts would have existed in different locations and with different intensities. Magnetotactic bacteria provide modern examples of how living organisms can interact directly with magnetic fields. These microscopic organisms contain chains of magnetite crystals that function as biological compasses, allowing the bacteria to navigate along magnetic field lines. The discovery of these organisms suggests that magnetic sensitivity may have been one of the earliest biological capabilities, possibly predating other sensory systems by hundreds of millions of years. Laboratory studies of mineral surfaces reveal that magnetic fields can influence the adsorption and organization of organic molecules on crystal faces. When organic compounds are exposed to mineral surfaces in the presence of magnetic fields, they show different patterns of molecular orientation and binding compared to the same molecules exposed to minerals without magnetic field influences. These effects could have been important in early Earth environments where organic synthesis was occurring on mineral surfaces in hydrothermal systems. The phenomenon of magnetic reconnection, observed in Earth's magnetosphere and in laboratory plasma experiments, demonstrates how magnetic fields can release stored electromagnetic energy in sudden bursts. During reconnection events, magnetic field lines break and reconnect in new configurations, releasing energy that accelerates charged particles to high velocities. Similar reconnection processes in the early Earth's electromagnetic environment could have provided bursts of energy that drove chemical reactions that would not otherwise have occurred. Ancient banded iron formations preserve records of the electromagnetic conditions that existed in Earth's early oceans. These rock formations consist of alternating layers of iron-rich and silica-rich minerals that may have precipitated in response to periodic changes in the ocean's electromagnetic environment. The regular banding pattern suggests that electromagnetic processes were operating with cyclic periodicity, possibly driven by variations in the Earth's magnetic field or by electromagnetic interactions with other celestial bodies. Electrochemical processes in modern hydrothermal systems show how electromagnetic activity can drive chemical reactions that would not occur under purely thermal conditions. When seawater interacts with hot volcanic rocks in the presence of electromagnetic fields, it undergoes reactions that produce hydrogen, methane, and other reduced compounds that can serve as energy sources for chemosynthetic organisms. Similar electrochemical processes in ancient hydrothermal systems may have provided the chemical energy necessary to drive the first steps toward biological metabolism. The discovery of electrical activity in thunderstorms on other planets suggests that electromagnetic phenomena are common features of planetary atmospheres throughout the solar system. Lightning has been detected in the atmospheres of Jupiter, Saturn, and Venus, indicating that the electrical processes that characterize terrestrial thunderstorms operate under a wide range of atmospheric conditions. During Earth's early history, when atmospheric composition was dramatically different, electrical activity in the atmosphere may have been more intense and more widespread than it is today. Radio emissions from Jupiter demonstrate how planetary magnetic fields can generate electromagnetic radiation that propagates through space. These radio signals are produced when charged particles interact with Jupiter's magnetic field, creating electromagnetic waves that can be detected by radio telescopes on Earth. Similar radio emissions from the early Earth would have created electromagnetic environments that extended far beyond the planet's atmosphere, possibly influencing chemical processes on the Moon and other nearby bodies. Studies of magnetic minerals in meteorites reveal that many small bodies in the solar system possess magnetic fields during their early history. Some meteorites contain magnetic minerals that were magnetized by planetary magnetic fields that no longer exist, providing evidence that electromagnetic activity was widespread throughout the early solar system. The electromagnetic environments created by these ancient magnetic fields may have influenced the chemistry of organic compounds in meteorites and comets before they were delivered to planetary surfaces. The phenomenon of magnetic levitation demonstrates how electromagnetic fields can overcome gravitational forces and influence the motion of small particles. In laboratory experiments, microscopic particles can be suspended and manipulated using carefully controlled magnetic fields, showing how electromagnetic forces could have influenced the behavior of organic molecules and microscopic structures in the electromagnetic environments of the early Earth. Yet, electromagnetic currents continue to flow through the planet's iron core, generating the magnetic field that extends into space and creates the complex electromagnetic environments that surround our world. Deep within the Earth, liquid iron moves in convective patterns that have persisted for billions of years, maintaining the dynamo process that creates the invisible electrical architecture of planetary space, providing the electromagnetic foundations that may have been essential for organizing the first tentative steps toward biological complexity in the primordial chemical experiments of the early Earth. Water moves through the world's oceans like liquid time itself, following currents that take 1,000 years to complete a single circuit around the globe. Deep beneath the waves, dissolved minerals travel these aquatic highways in concentrations so dilute they seem insignificant. Yet over the vast scales of oceanic circulation, these microscopic chemical travelers accumulate in patterns that create the concentrated reservoirs of life's essential building blocks. The chemistry of the ancient oceans operated with the same patient circulation, slowly gathering the molecular ingredients necessary for the first experiments in biological complexity. The global thermohaline circulation system operates through differences in water density created by variations in temperature and salinity. Cold. Salty water sinks in the polar regions and flows along the ocean floor toward the equator, while warm surface water moves poleward to replace it. This circulation pattern, sometimes called the global conveyor belt, transports not only water but also dissolved gases, nutrients, and trace elements throughout the world's ocean basins. The complete circulation cycle takes roughly 1,000 years, meaning that water molecules currently sinking in the North Atlantic will not return to the surface until they have traveled through the depths of the Pacific and Indian Oceans. Modern oceanographic studies reveal the extraordinary complexity of deep ocean chemistry. Seawater contains dissolved ions of virtually every element in the periodic table, from common constituents like sodium and chloride to trace elements like molybdenum, vanadium, and rare earth elements that exist in concentrations of parts per billion or less. Despite these low concentrations, the vast volume of the oceans means that the total inventory of dissolved elements is enormous. The oceans contain more than 50 million tons of dissolved gold. For example, though it is distributed so thinly that extraction is not economically feasible, the residence time of different elements in seawater varies dramatically, from thousands of years for biologically active elements like phosphorus and nitrogen to millions of years for chemically inert elements like sodium. These different residence times create complex patterns of chemical cycling as ocean currents transport dissolved materials between different marine environments. Elements with short residence times are quickly removed from seawater by biological processes or chemical precipitation, while elements with long residence times accumulate to higher concentrations over geological time. The mystery lies in understanding how ancient ocean circulation patterns concentrated the specific combinations of chemical elements necessary for the emergence of life. Computer models of early Earth-ocean chemistry suggest that hydrothermal circulation systems may have created localized regions of enhanced chemical diversity where unusual combinations of dissolved elements could interact in ways that promoted the formation of complex organic molecules. These chemical oases would have been connected by ocean currents that transported organic compounds between different marine environments. In the deep Pacific Ocean, researchers study manganese nodules that have been growing on the seafloor for millions of years through the slow precipitation of metals from seawater. These potato-sized concretions contain high concentrations of manganese, iron, nickel, copper, and cobalt that have been extracted from seawater by bacterial and chemical processes operating over geological timescales. The nodules provide direct evidence of how ocean circulation can concentrate trace elements that are present in seawater at extremely low concentrations. Only took a few billion years of oceanic circulation to establish the chemical reservoirs that would support the emergence and evolution of marine life. The geochemical models suggest, with the kind of chemical patience that makes tidal cycles seem rushed, only took countless circuits of deep water around the globe to transport and concentrate the dissolved phosphorus, nitrogen, sulfur, and trace metals that living organisms would eventually learn to extract from seawater for building proteins, nucleic acids, and metabolic cofactors. Only took the slow chemistry of oceanic mixing to create the chemical gradients and concentration patterns that would provide the raw materials for 4 billion years of biological innovation. The phenomenon of hydrothermal circulation demonstrates how heat from Earth's interior drives chemical processes that alter seawater composition. At mid-ocean ridges, cold seawater penetrates into newly formed oceanic crust, where it is heated to temperatures exceeding 350 degrees before being expelled back into the ocean through hydrothermal vents. This circulation process strips metals from volcanic rocks and concentrates them in hydrothermal fluids that create unique chemical environments when they mix with cold seawater. Isotopic studies of ancient marine sediments reveal how ocean chemistry has changed over geological time. The isotopic compositions of carbon, sulfur, and strontium in marine carbonates and sulfates preserve records of the chemical conditions that existed in ancient oceans. These records show that seawater chemistry has undergone dramatic changes, including periods when the oceans were more acidic, more reducing, or contained different concentrations of dissolved nutrients compared to modern conditions. The biological pump demonstrates how marine organisms influence ocean chemistry by transporting elements between surface and deep waters. Phytoplankton in the surface ocean extract carbon dioxide, nutrients, and trace elements from seawater during photosynthesis. When these organisms die and sink to the deep ocean, they transport these elements to depth, where they are released back into seawater through bacterial decomposition. This biological transport creates vertical gradients in chemical composition that affect the global cycling of elements essential for life. Paleoceanographic studies of ancient black shales reveal periods in Earth's history when ocean circulation was dramatically different from today. These organic-rich sedimentary rocks formed during periods when deep ocean waters became depleted in oxygen, creating conditions where organic matter could accumulate on the seafloor without being completely decomposed. The formation of black shales required changes in ocean circulation patterns that reduced the transport of oxygen to deep waters, demonstrating how circulation changes can have profound effects on marine chemistry. The discovery of extremophile organisms living in deep ocean sediments shows that biological processes can operate in chemical environments that were once thought to be sterile. These organisms survive in sediments where organic matter concentrations are extremely low and where chemical energy sources are limited to trace amounts of dissolved compounds. Their existence demonstrates how ocean circulation can maintain chemical gradients that support life even in the most chemically challenging marine environments. Deep-sea brine pools provide modern examples of how density differences can create long-lasting chemical anomalies in marine environments. These underwater lakes consist of extremely salty water that is denser than normal seawater, creating distinct boundaries between different water masses. The brine pools can persist for decades or centuries, maintaining their unique chemistry while being slowly mixed with surrounding seawater by deep ocean currents. The chemical composition of seafloor hydrothermal deposits reveals how ocean circulation transports dissolved metals over vast distances before concentrating them in localized deposits. Massive sulfide deposits at hydrothermal vents contain high concentrations of copper, zinc, lead, silver, and gold that were transported in solution from volcanic rocks hundreds of miles away. The formation of these deposits requires the precise intersection of hydrothermal circulation with deep ocean currents that transport metal-bearing fluids to sites where chemical precipitation can occur. Sediment core studies from the deep ocean reveal how changes in ocean circulation affect the distribution of chemical elements in marine sediments. Cores from the Atlantic Ocean show periodic changes in the concentrations of trace elements that correlate with changes in deep water circulation patterns driven by climate variations. These records demonstrate how ocean circulation changes can redistribute chemical elements among different marine environments over timescales of thousands to millions of years. The phenomenon of oceanic anoxic events in Earth's history shows how disruptions in ocean circulation can create global changes in marine chemistry. During these events, which lasted for hundreds of thousands of years, large portions of the world's oceans became depleted in oxygen, leading to the widespread deposition of organic-rich sediments. The events appear to have been triggered by changes in ocean circulation that reduced the mixing between surface and deep waters. Micronutrient distributions in modern oceans demonstrate how ocean circulation controls the availability of chemical elements essential for marine life. Iron, for example, is present in extremely low concentrations in most seawater, but is essential for photosynthesis and other biological processes. Ocean currents transport iron-rich water from coastal regions and hydrothermal vents to the open ocean, creating patterns of iron availability that influence the productivity of marine ecosystems. Yet the oceans continue their ancient circulation, carrying dissolved chemistry through the three-dimensional maze of currents that connect every drop of seawater to every other drop over the course of centuries. Deep beneath the waves, the patient chemistry of oceanic mixing continues to operate with the same fundamental processes that concentrated the raw materials of life billions of years ago, transporting molecular building blocks through the vast aquatic circulation system that has provided the chemical foundation for marine life throughout Earth's history. Atmospheric pressure changes by amounts so small they escape human notice. Yet over millions of years, these microscopic variations in the weight of air sculpt landscapes and determine the depths at which life can survive beneath the surface of ancient seas. The atmosphere presses down on Earth's surface with a force of nearly 15 pounds per square inch. But this pressure is not constant. It fluctuates with weather patterns, seasonal cycles, and long-term climate changes in ways that create subtle but persistent influences on geological processes and biological evolution over timescales that span entire geological eras. The relationship between atmospheric pressure and altitude follows an exponential decay curve, with pressure decreasing by roughly half for every 18,000 feet of elevation gain. This relationship means that small changes in global atmospheric pressure can shift the effective altitude of any location on Earth's surface, altering the conditions for life in ways that accumulate over geological time. During periods when atmospheric pressure was higher than today, organisms could survive at greater depths in the ocean because the increased surface pressure enhanced the solubility of oxygen and other gases in seawater. Modern atmospheric pressure measurements reveal variations that operate on multiple time scales, from daily fluctuations caused by thermal tides in the atmosphere to decadal changes associated with climate oscillations like El Niño and the North Atlantic Oscillation. Barometric pressure records extending back several centuries show that these variations can persist for years or decades, creating prolonged periods of slightly elevated or reduced atmospheric pressure that affect weather patterns and ocean circulation over large geographic regions. Paleoclimate studies suggest that Earth's atmospheric pressure has varied significantly over geological history. During the Carboniferous period, roughly 300 million years ago, atmospheric oxygen concentrations were much higher than today, potentially creating total atmospheric pressures that were 35% greater than modern levels. These higher pressures would have allowed oxygen to penetrate deeper into soils and sediments, creating oxidizing conditions at depths where reducing conditions exist today and potentially affecting the preservation of organic matter in ancient sedimentary rocks. The mystery lies in understanding how these long-term pressure variations influence the evolution of life, particularly the transition from marine to terrestrial environments. Higher atmospheric pressures would have made it easier for early land animals to extract oxygen from the air, potentially facilitating the evolution of large body sizes and complex respiratory systems. Lower atmospheric pressures, by contrast, would have limited the effectiveness of air-breathing respiratory systems and may have constrained the maximum size that terrestrial organisms could achieve. In the Green River Formation of Wyoming, paleontologists study exceptionally preserved fossils from an ancient lake system that existed roughly 50 million years ago. The fine-scale preservation of organic structures in these fossils suggests that the lake bottom environments experienced unusual chemical conditions that prevented normal decay processes. Some researchers propose that these conditions resulted from enhanced atmospheric pressure that increased the solubility of gases in the lake water, creating chemical environments that inhibited bacterial decomposition. Only took a few billion years of atmospheric pressure variations to help carve the landscape patterns that determine where water flows, where soils develop, and where different types of organisms can establish viable populations. The geological evidence suggests, with the kind of barometric patience that makes storm systems seem momentary, only took countless cycles of slightly elevated and reduced atmospheric pressure to influence the depth penetration of weathering processes that break down rocks and create the mineral components of soil systems. Only took the patient pressure of air molecules to help establish the altitudinal and depth limits within which early life could experiment with different physiological strategies for gas exchange and metabolic energy production. The phenomenon of atmospheric loading demonstrates how changes in air pressure can directly influence solid Earth processes. When atmospheric pressure increases over a region, the additional weight can cause measurable subsidence of the land surface, while decreasing pressure allows the surface to rebound upward. These effects are small, typically measured in millimeters, but they can affect the flow of groundwater and the stability of geological formations over long periods of time. Laboratory experiments on rock weathering show that atmospheric pressure influences the rate at which chemical reactions proceed between air and mineral surfaces. At higher pressures, gases like oxygen and carbon dioxide are more readily absorbed into water films that coat mineral grains, accelerating the chemical reactions that break down rocks and release dissolved ions. These pressure effects on weathering rates could have influenced soil formation processes and the delivery of nutrients to early terrestrial ecosystems. The solubility of gases in water increases with pressure according to Henry's law, meaning that changes in atmospheric pressure directly affect the chemical composition of natural waters. During periods of elevated atmospheric pressure, rivers, lakes, and shallow marine environments would have contained higher concentrations of dissolved oxygen, carbon dioxide, and other atmospheric gases. These changes in aquatic chemistry could have affected the metabolism and distribution of early aquatic organisms. Paleosol studies reveal how ancient atmospheric conditions are preserved in fossil soil profiles. These buried soils contain chemical and mineralogical signatures that reflect the atmospheric composition and pressure conditions that existed when the soils were forming. Some ancient paleosols show evidence of deeper oxidation zones than would be expected under modern atmospheric conditions, suggesting that higher atmospheric pressure in the past allowed oxygen to penetrate deeper into soil profiles. The discovery of gas-filled inclusions in ancient minerals provides direct evidence for atmospheric pressure conditions in the geological past. These microscopic bubbles of ancient atmosphere, trapped during mineral crystallization, can be analyzed to determine the pressure and composition of ancient air. Studies of gas inclusions in amber and other minerals suggest that atmospheric pressure has varied by tens of % over the past 100 million years. Hydrostatic pressure effects in deep marine environments demonstrate how pressure influences biological processes at the cellular level. As pressure increases with depth in the ocean, it affects the structure and function of proteins, cell membranes, and other biological molecules. Organisms that live at great depths have evolved specialized adaptations to high-pressure environments, and changes in atmospheric pressure would have altered the effective pressure environment throughout the ocean water column. The atmospheric pressure gradient between different elevations creates patterns of gas exchange that influence biological processes in mountain environments. At high altitudes, where atmospheric pressure is lower, the partial pressure of oxygen is reduced, making it more difficult for organisms to extract sufficient oxygen from the air. During periods when overall atmospheric pressure was different, the altitude at which these oxygen limitation effects became significant would have been shifted up or down accordingly. Volcanic degassing processes are influenced by atmospheric pressure through their effects on gas bubble formation and magma viscosity. Lower atmospheric pressure allows dissolved gases in magma to exsolve more readily, potentially leading to more explosive volcanic eruptions. Higher atmospheric pressure has the opposite effect, favoring more effusive eruptions. These pressure effects on volcanic activity could have influenced the rate of atmospheric gas input from volcanic sources over geological time. The carbonate compensation depth in the ocean, the depth below which calcium carbonate dissolves rather than accumulates, is influenced by the pressure-dependent solubility of carbon dioxide in seawater. Changes in atmospheric pressure would have affected this depth, altering the distribution of carbonate sediments on the seafloor and affecting the preservation of calcifying organisms in the fossil record. Studies of modern extremophile organisms reveal how life adapts to unusual pressure conditions. Barophilic bacteria that thrive under high pressure conditions show specialized cellular machinery that functions optimally at elevated pressures. The existence of these pressure-adapted organisms suggests that atmospheric pressure variations in Earth's history may have influenced the evolution of fundamental cellular processes. The phenomenon of pressure-induced phase transitions in minerals demonstrates how changes in pressure can alter the physical properties of Earth materials. Some minerals undergo structural changes when subjected to different pressure conditions, affecting their density, hardness, and chemical reactivity. Long-term changes in atmospheric pressure could have influenced these phase transition boundaries in near-surface environments. Gas exchange processes in plant stomata are directly influenced by atmospheric pressure through their effects on the diffusion rates of carbon dioxide and water vapor. Changes in atmospheric pressure would have affected the efficiency of photosynthesis and transpiration in early land plants, potentially influencing the evolution of stomatal regulation mechanisms and plant water use strategies. Yet atmospheric pressure continues to exert its subtle influence on every surface process operating on the planet, pressing down on landscapes and seascapes with forces that vary by tiny amounts from day to day and season to season, but which accumulate over geological time to help shape the physical and chemical environments where life conducts its ongoing experiments in biological innovation and adaptation to the ever-changing conditions of Earth's surface and shallow subsurface environments. Light falls upon the ancient Earth in wavelengths that carry more than simple illumination, creating photochemical laboratories in the early atmosphere where solar radiation drives reactions that operate over geological timescales. 4 billion years ago, as ultraviolet radiation streams through an atmosphere almost devoid of oxygen, photons with energy sufficient to break molecular bonds trigger chemical cascades that transform the composition of air and water in ways that accumulate over millions of years, establishing the photochemical foundations for processes that will eventually support the emergence of life. The electromagnetic spectrum of solar radiation encompasses wavelengths from high-energy gamma rays to low-energy radio waves, but only certain portions of this spectrum reach Earth's surface in significant quantities. The atmosphere acts as a selective filter, absorbing some wavelengths while allowing others to pass through. During Earth's early history, when atmospheric composition was dramatically different from today, different wavelengths of solar radiation would have reached the surface, creating photochemical environments that no longer exist anywhere on the modern Earth. Modern studies of atmospheric photochemistry reveal the complex networks of reactions that occur when solar radiation interacts with trace gases in the atmosphere. Ultraviolet radiation breaks apart molecules of water vapor, carbon dioxide, methane, and other atmospheric constituents, creating highly reactive atomic and molecular fragments that can recombine in numerous ways. These photochemical reactions operate continuously wherever sunlight penetrates the atmosphere, but their cumulative effects become apparent only over timescales of years to centuries. The ozone layer in Earth's stratosphere demonstrates how photochemical processes can create protective barriers that alter the radiation environment at the planet's surface. Ozone forms when ultraviolet radiation splits molecular oxygen into atomic oxygen, which then combines with other oxygen molecules to form the three-atom ozone molecule. This ozone absorbs much of the harmful ultraviolet radiation that would otherwise reach Earth's surface. But during the early Earth's history, when oxygen was scarce, no significant ozone layer existed. The mystery lies in understanding how the photochemical processes operating in Earth's early atmosphere contributed to the formation of organic compounds that could serve as building blocks for life. Laboratory experiments show that when mixtures of simple gases like methane, ammonia, and water vapor are exposed to ultraviolet radiation, they produce a variety of organic molecules, including amino acids, nucleotide bases, and other compounds essential for biological chemistry. The early Earth's atmosphere may have functioned as a vast photochemical reactor, continuously producing organic compounds through radiation-driven processes. In the Pilbara region of Western Australia, geologists study rock formations that preserve chemical evidence of Earth's early atmospheric composition. These ancient rocks contain unusual sulfur isotope signatures that could only have formed through photochemical reactions involving sulfur dioxide gas in an atmosphere with very low oxygen content. The isotopic patterns provide direct evidence that photochemical processes operating billions of years ago were fundamentally different from those that operate in the modern atmosphere. Only took a few billion years of continuous solar irradiation to establish the photochemical cycles that regulate atmospheric composition today. The atmospheric chemistry models suggest, with the kind of photochemical patience that makes seasonal changes in daylight seem rapid, only took countless photons breaking countless molecular bonds to gradually transform the reducing atmosphere of the early Earth into the oxygen-rich atmosphere that characterizes our planet today. Only took the patient accumulation of radiation-driven chemistry to create the photochemical infrastructure that would eventually enable photosynthetic organisms to harness solar energy for biological processes. The phenomenon of photodissociation demonstrates how solar radiation can break apart even stable molecules when sufficient energy is applied over geological timescales. Water molecules in the upper atmosphere are continuously broken apart by ultraviolet radiation, creating hydrogen and oxygen atoms that follow different chemical pathways. The hydrogen, being lighter, tends to escape to space, while the oxygen remains in the atmosphere where it can participate in other chemical reactions. Photochemical smog formation in modern urban environments provides insights into how complex organic chemistry can result from the interaction of solar radiation with trace atmospheric constituents. When sunlight acts on mixtures of nitrogen oxides and hydrocarbon compounds, it creates a complex brew of organic molecules, including aldehydes, organic acids, and aerosol particles. Similar photochemical processes in the early Earth's atmosphere, operating with different starting materials, may have produced different but equally complex organic chemistry. The discovery of organic compounds in the atmospheres of other planets and moons demonstrates that photochemical synthesis of organic molecules is a widespread process throughout the solar system. Titan. Saturn's largest moon has an atmosphere rich in methane and nitrogen that undergoes photochemical reactions driven by solar ultraviolet radiation and energetic particles from Saturn's magnetosphere. These reactions produce complex organic molecules that fall to Titan's surface as a kind of organic snow. Laboratory studies of prebiotic photochemistry show how the wavelength distribution of radiation affects the types of organic compounds that can be synthesized. Ultraviolet radiation with wavelengths shorter than 280 nanometers can break the carbon-hydrogen bonds in methane and other simple organic molecules, creating reactive fragments that can form longer molecular chains. Different wavelengths produce different chemical products, suggesting that changes in the solar ultraviolet spectrum over geological time could have influenced the evolution of atmospheric organic chemistry. The role of atmospheric aerosols in modifying photochemical processes demonstrates how small particles can have large effects on radiation-driven chemistry. Aerosol particles scatter and absorb solar radiation, altering the intensity and wavelength distribution of light that reaches different altitudes in the atmosphere. During periods of intense volcanic activity in Earth's early history, when atmospheric aerosol concentrations were higher, photochemical reaction rates and pathways would have been significantly different from those that operate today. Seasonal variations in solar radiation intensity and duration create annual cycles in atmospheric photochemistry that affect the production and destruction of trace atmospheric constituents. At high latitudes, where seasonal variations in daylight are most extreme, photochemical processes shut down almost entirely during winter months and reach maximum intensity during summer. Over geological time, changes in Earth's orbital parameters have altered these seasonal patterns, creating long-term variations in photochemical processing rates. The discovery of photochemical isotope effects reveals how radiation-driven processes can selectively favor certain isotopic forms of elements over others. When carbon dioxide molecules containing different carbon isotopes are exposed to ultraviolet radiation, the molecules containing the lighter carbon-12 isotope are slightly more likely to be broken apart than those containing the heavier carbon-13 isotope. This selective photodissociation can create isotopic signatures in atmospheric and geological materials that preserve records of ancient photochemical processes. Photochemical models of early Earth atmospheric evolution suggest that radiation-driven chemistry played a crucial role in establishing the chemical gradients between the atmosphere, oceans, and solid Earth that drive many geological processes. The continuous photochemical processing of atmospheric gases creates chemical species that are more reactive than their starting materials, enhancing the rates of weathering, ocean chemistry, and sedimentary processes that shape Earth's surface environment. The study of photochemical processes in laboratory simulations of early Earth conditions reveals how the intensity and spectrum of solar radiation affect organic synthesis rates. When simple atmospheric gases are exposed to radiation sources that mimic the young sun's output, they produce different organic compounds than when exposed to radiation that mimics the modern sun. These differences in photochemical products could have influenced the types of organic compounds available for early biological processes. Atmospheric escape processes demonstrate how photochemical reactions can lead to permanent loss of atmospheric constituents to space. When water vapor is photodissociated in the upper atmosphere, the resulting hydrogen atoms can achieve sufficient velocity to escape Earth's gravitational field. Over geological time, this photochemically driven atmospheric escape has contributed to changes in the planet's water inventory and atmospheric composition. The interaction between photochemical processes and biological evolution becomes apparent in the geological record through chemical signatures that reflect the coevolution of atmospheric chemistry and life. The rise of oxygen-producing photosynthesis fundamentally altered Earth's photochemical environment by introducing large quantities of oxygen that created new reaction pathways and changed the wavelengths of solar radiation that could penetrate to Earth's surface. Studies of organic compounds preserved in ancient sedimentary rocks reveal how photochemical products from the atmosphere were incorporated into geological materials over Earth's history. Some of these compounds show isotopic signatures that can only be explained by photochemical processes operating in atmospheric compositions that differed significantly from modern conditions, providing direct evidence for the evolution of Earth's photochemical environment over geological time. Yet solar radiation continues to drive photochemical reactions throughout Earth's atmosphere, breaking molecular bonds and creating reactive species that participate in the complex networks of atmospheric chemistry that regulate air quality. Climate and the chemical connections between Earth's atmosphere, oceans, and biosphere. The photochemical laboratory of Earth's atmosphere operates continuously, powered by the same solar energy that has been driving atmospheric chemistry for billions of years, creating the radiation-driven chemical processes that helped establish the conditions necessary for life to emerge and evolve on our planet. In the vast emptiness between planetary influences, Earth develops its most distinctive characteristics through processes so gradual they occur in the silence that exists between the gravitational voices of other worlds. Here, in the cosmic quiet that fills the spaces where Jupiter's pull weakens and Mars's influence fades, the planet's most subtle systems find room to operate according to their own internal rhythms. These are the processes that require astronomical solitude to achieve their full expression, chemical and physical phenomena that can only unfold when freed from the competing influences of neighboring worlds. The orbital mechanics of the solar system create regions of gravitational calm where Earth's own forces can dominate without interference from external influences. These Lagrange points and gravitational null zones exist at specific mathematical locations where the combined gravitational fields of multiple bodies create regions of relative stability. Within these zones of cosmic quiet, particles of dust and gas can accumulate over millions of years, following trajectories determined primarily by Earth's own gravitational field rather than the competing influences of other planets. Modern space missions have revealed that these apparently empty regions of space contain complex populations of dust particles, charged atoms, and organic molecules that interact with Earth's magnetosphere in ways that were completely unknown until the space age. The solar wind, the stream of charged particles flowing outward from the sun, creates bow shocks and wake regions around planetary magnetic fields, establishing zones of electromagnetic quiet where different physical processes can operate without the turbulent mixing that characterizes most of interplanetary space. Geochemical studies of the most ancient rocks on Earth reveal isotopic signatures that appear to result from processes that operated in isolation from the chemical influences of other planetary bodies. These signatures suggest that during certain periods of Earth's early history, the planet's chemical evolution proceeded according to purely internal dynamics, free from the external inputs of cosmic debris that characterized other periods. The chemical fingerprints of these isolated periods are preserved in mineral formations that show unusual isotopic compositions. The mystery lies in understanding how these periods of cosmic isolation influence the development of Earth's unique characteristics, particularly the chemical conditions that made life possible. Computer models suggest that planets require periods of relative solitude to develop stable chemical systems that can support complex organic chemistry over geological timescales. Too much external input from cosmic sources can disrupt the delicate chemical balances necessary for biological processes to establish themselves. In the deep ocean sediment cores recovered from the most remote regions of the Pacific Basin, Paleoceanographers find layers that formed during periods when cosmic dust input to Earth's atmosphere was unusually low. These sedimentary layers show chemical compositions that reflect purely terrestrial processes, uncontaminated by the cosmic chemistry that characterizes most of Earth's geological record. The chemical signatures preserved in these layers provide insights into how Earth's internal systems operate when freed from external cosmic influences. Only took a few billion years of alternating cosmic interaction and cosmic solitude to establish the chemical complexity that characterizes Earth's surface environment today. The geochemical models suggest, with the kind of planetary patience that makes even continental drift seem hurried, only took countless orbital cycles through regions of varying cosmic influence to create the chemical diversity that allowed early life to experiment with different metabolic strategies and eventually develop the biochemical innovations that would lead to complex multicellular organisms. Only took the patient rhythm of cosmic silence and cosmic interaction to provide Earth with both the external chemical inputs and the internal processing time necessary to develop its unique biosphere. The phenomenon of atmospheric escape demonstrates how planets must achieve a delicate balance between retaining essential atmospheric constituents and losing excess materials to space. During periods when Earth passes through regions of intense cosmic bombardment, atmospheric loss rates increase dramatically. During periods of cosmic quiet, atmospheric loss rates decrease, allowing the planet to retain volatile compounds that might otherwise be stripped away by energetic cosmic processes. Laboratory studies of isotopic fractionation show how internal planetary processes can create chemical signatures that are distinct from those produced by cosmic inputs. When rocks undergo weathering, metamorphism, or other internal geological processes in the absence of external contamination, they develop isotopic patterns that reflect purely terrestrial chemical evolution. These patterns can be detected in ancient rock formations and used to identify periods when Earth's chemical evolution proceeded without significant cosmic interference. The discovery of unique mineral phases in certain ancient rock formations suggests that some geological processes can only occur under conditions of cosmic isolation. These minerals form through chemical reactions that require very specific temperature, pressure, and chemical conditions that can only be maintained when external cosmic inputs are minimized. The presence of these minerals in the geological record provides evidence for periods when Earth's internal systems operated without significant external perturbation. Paleomagnetic studies reveal that Earth's magnetic field undergoes periodic variations that may be related to the planet's passage through different regions of cosmic space. During periods when Earth encounters regions of high cosmic particle density, the planet's magnetic field experiences increased stress and may undergo more frequent reversals. During periods of cosmic quiet, the magnetic field becomes more stable, allowing internal dynamo processes to operate with greater consistency. The biological implications of cosmic quiet periods become apparent in the fossil record through episodes of rapid biological innovation that correlate with times when cosmic bombardment rates were low. These periods of biological experimentation appear to have occurred when Earth's surface environments were relatively stable and free from the disruptive effects of frequent cosmic impacts. The correlation suggests that periods of cosmic solitude may be necessary for complex biological systems to develop and diversify. Studies of lunar impact crater distributions provide insights into the timing and intensity of cosmic bombardment episodes that have affected the Earth-Moon system throughout its history. The lunar surface preserves a record of impact events that extends back to the earliest periods of solar system history, revealing patterns of cosmic bombardment that have varied dramatically over geological time. Periods of low impact rates on the Moon correspond to times when Earth would also have experienced cosmic quiet. The chemistry of the most ancient zircon crystals, found in terrestrial rocks, reveals isotopic signatures that appear to record chemical processes operating under conditions very different from those that exist today. Some of these signatures suggest that the early Earth experienced periods when its chemical evolution was dominated by internal processes rather than external cosmic inputs. These chemical fingerprints provide direct evidence for periods of cosmic isolation in Earth's early history. Atmospheric modeling studies show how periods of reduced cosmic dust input affect global climate patterns and atmospheric chemistry. When cosmic dust input decreases, the atmosphere becomes more transparent to solar radiation, potentially affecting global temperatures and photochemical reaction rates. These atmospheric changes create feedback loops that can influence biological productivity and chemical weathering rates over geological timescales. The phenomenon of biological clock synchronization reveals how cosmic influences can affect even the most fundamental biological processes. Many organisms have internal biological rhythms that are synchronized to cosmic cycles, including daily solar cycles and lunar cycles. During periods of cosmic quiet, when these external timing signals are reduced, biological systems must rely more heavily on internal timing mechanisms, potentially leading to different patterns of biological activity and evolution. Deep crustal studies reveal that some of Earth's most distinctive geological features formed during periods when the planet's internal processes operated with minimal external influence. Certain types of ore deposits, unusual rock formations, and distinctive geological structures appear to have formed when Earth's internal chemical and physical systems could operate without the disruption of frequent cosmic impacts or other external perturbations. The isotopic composition of atmospheric gases preserved in ancient ice cores and rock formations shows periodic variations that appear to correlate with Earth's passage through different regions of cosmic space. During periods when the planet encounters regions of cosmic quiet, atmospheric isotopic compositions show signatures that reflect primarily internal atmospheric processes rather than external cosmic inputs. Studies of extremophile organisms living in Earth's most isolated environments provide insights into how life can develop and persist in the absence of external inputs. These organisms, found in deep caves, isolated underground environments, and other locations cut off from external influences, show metabolic strategies and biochemical innovations that may be similar to those that developed during Earth's periods of cosmic isolation billions of years ago. Yet Earth continues its journey through the cosmos, alternately encountering regions of intense cosmic activity and regions of relative cosmic silence, each environment contributing to the planet's ongoing chemical and biological evolution. In the spaces between planetary influences, where gravitational forces balance and cosmic bombardment rates decrease, Earth's internal systems find the solitude necessary to develop their most subtle and sophisticated processes, creating the quiet foundations for the complex planetary systems that support the continuing evolution of life in the patient silence that exists between the voices of distant worlds. The forces that shaped our world continue their quiet work in this very moment, as invisible and patient as they have been for billions of years. Somewhere beneath your feet, the solid rock of continents flexes by micrometers in response to Jupiter's distant pull. High above, charged particles from Mars's vanishing atmosphere drift through the magnetosphere, adding their chemical whispers to Earth's upper air. The moon retreats by another fingernail's width this year, lengthening our days by milliseconds that accumulate like grains of sand towards some unimaginable future. In the depths of ocean trenches, water that last saw sunlight 1,000 years ago carries dissolved minerals on currents so slow they make glaciers seem restless. Deep within the planetary core, Liquid iron moves in patterns that generate the magnetic fields stretching tens of thousands of miles into space, creating the electromagnetic architecture that helped organize the first tentative experiments in biological chemistry billions of years ago. Crystals in mountain ranges hum with piezoelectric frequencies too low for any ear to detect, converting the patient stress of continental drift into electrical fields that influence the chemistry of groundwater flowing through microscopic fractures in ancient stone. The atmospheric rivers that once carried moisture across continents that no longer exist have given way to new circulation patterns, but the same fundamental processes continue to transport chemistry through three-dimensional highways of moving air. Tidal forces, gentler now than they were when the moon hung closer in ancient skies, still raise and lower the solid Earth by centimeters, creating stress patterns that propagate through the planet's interior like the echoes of some vast, slow heartbeat. These are the quiet forces we overlooked, the patient architects of worlds, the invisible sculptors of continents and atmospheres, and the chemical conditions necessary for life. They operate in the spaces between human perception and human timescales, in the realm where millions of years feel like moments, and where the slightest influences, accumulated over geological ages, become the foundations of everything we see around us. Tonight, as you rest, these forces continue their ancient work with the same steady persistence they have maintained since the solar system was young. The planet breathes with tidal rhythms, rings with seismic music, and drifts through cosmic space on currents of gravity and time that connect every grain of sand to every distant star through the patient mathematics of force and motion and the endless, quiet creativity of deep time.